Okay, we'll start today's session. The first talk is for Carlos dos Santos Gama. The title is the SDA harvesting model in rural environments, the effect of LEFX model local practice on profit optimization. Is here or is it? Okay. Carlos, you are here.
Hi, I'm here also for the
Okay.
next talk. Good
Yes.
afternoon.
Only here in Costa Rica, Teatro en Portugal, or Europe.
Good afternoon. Good morning.
Hello, good morning to everyone.
Yeah, good afternoon for us. For them is not.
Who's gonna, Carlos, are you going to give the talk?
Yes, yes.
Okay, you're ready.
Are you ready? Okay, so can I share the screen?
Sure.
Let's see what, here it is. Great. Let's see this side. Okay, I'm ready. Can you hear me?
Yes, yeah.
Yeah, should I start?
Yes,
Or
please.
wait? Okay, thank you so much.
You represented, but probably you were not listening. So.
Sorry, I couldn't hear.
Yeah, you were already presented.
The sound is quite bad. Okay, well, I'll start it. Well, thank you so much for the presentation, and also I would like to congratulate our colleagues organizing this workshop for its nice work on trying to join together the two people from the two centers. And yeah, it's a very nice idea, and I'm glad to be here today. Well, let me start by saying the title is Stochastic Differential Equation Harvesting Models in Random Environments, and I'm talking about the effect of Ali effects on the population, model robust properties, and issues of profit optimization in harvesting. And that's a joint work with Nuno Brites and Clara Carlos. Well, when you want to model the growth of a fish population or some other harvested population in a randomly varying environment, we could use stochastic differential equations. First of all, we want to show general properties that apply to a wide variety of populations, irrespective of their specifics of growth dynamics. And so we use general growth models to obtain general results on extinction and on sustainability, that is, on existence of a stochastic equilibrium with a stationary density. And we have all results on general density-independent growth models without Ali effects and with general autonomous harvesting effort. More recently, we have results on models, general models with Ali effects, but without taking out the harvesting. And finally, joining the two together, we're talking about general models with Ali effects and also with harvesting, having general autonomous harvesting effort. The second part is about showing results on profit optimization in harvesting for particular growth models, because we want to make numerical comparisons. We have to use specific models. And we use logistic and Compert's model in case there are no Ali effects in the population. In case there are Ali effects in population, we use the logistic-like model with Ali effects. And then we make comparisons of several harvesting policy types, but of course, we're just showing you a few today because we don't have time to show them all. Now, let's look first at the general deterministic model without harvesting, okay? So we have the growth rate of the population. Population is x of t at time t. That's the per capita growth rate of the population. It's just a function of population size. And usually, if the only thing matter is the resource limitation, we know that as the population gets larger, the amount of resources available per individual for its growth and reproduction, survival and reproduction is per capita growth rate, therefore, should decrease. And so we should have a strictly decreasing function f. Okay, now, example, logistic model is the classical example in which the average per capita natural growth rate looks like that. Okay, carrying capacity K here, strictly decreasing, but there are other models, alternative models. And then if we have Ali effects, the situation changes. Ali effects cause a depression in the growth rate for small population sizes, say for sizes of smaller than some L value, and maybe due, for instance, to difficulty of the individuals to find many partners because the population is widespread, maybe, and they're few, maybe they have a difficulty in mounting a collective defense against their predators because they're few, or on the contrary, if they are predators, in mounting a collective attack against prey. So in that case, the growth rate, per capita growth rate, gets depressed in what would be if only resource limitation would apply. So for small populations, and of course the effect is worse the smaller the population is. So the per capita growth rate, instead of going down, I think with increasing population, will go up. So we have this effect here going up, and then resource limitation are more relevant than Ali effects, and then it goes down, depending on whether it prevents. So we have this model, the logistic-like model with Ali effects, with a different parameterization to make it comparable with this one. And the parameter A measures the intensity of Ali effects. Of course, if we have a depression in the growth rate that is not big enough so that at small population sizes we still have a positive growth rate, then we have weak Ali effects. If on the contrary, we have a negative growth rate, then we have strong Ali effects. Okay, that's the L value I mentioned before. And now we're going to look at these models and make some assumptions. We want general models. Okay, we have general assumptions on the function f, the per capita growth rate, natural growth rate. It's of, well, technical assumptions, the no immigration assumption, the resource limitation assumption that very large populations should have a negative growth rate. And in the case there are Ali, we need additional assumptions due to in the absence of Ali effects, you only have resource limitations, so F should be strictly decreasing. And if it's positive for small population sizes, we know there is a carrying capacity above which we have negative growth rates, and for populations below which we have positive growth rates. Now, in the presence of Ali effects, of course, due to the depression, we have this additional technical assumption to still assume there is a carrying capacity above which we have negative growth rates. But now there is an L value such that function f is only strictly decreasing after, for larger populations than L. For smaller populations than L, then Ali effects prevail over resource limitations, and we have a strictly increasing function. Now, let's look at what happens if the population lives in a randomly varying environment. Well, in that case, this function f is just the per capita average natural growth rate, actually arithmetic average because I'm using Ito calculus and Ito stochastic differential equations. Of course, that's the average natural growth rate per capita. Then we have to, the actual growth rate is going to be its average plus the deviations from average induced by environmental fluctuations, which we assume can be approximated by a white noise multiplied by a noise intensity parameter sigma. Now, we still assume now we are harvesting the population, fishing, for instance, and then we have to subtract the fishing mortality rate, which is proportional to the fishing effort we exert. I'm assuming that the fishing effort is a function of population size, so we have an autonomous model, and the proportionality constant is called catchability. So this term is the harvesting mortality rate or fishing mortality rate, and if you multiply it by the population size, you have the amount of fish captured per unit time. Well, what assumptions are we making on this function, this fishing effort E? But basically just very technical and simple assumptions, so it's very general. Well, this stochastic differential equation can be written in the standard format you see in the literature if you use the standard Wiener process that is the integral of white noise. Well, let's examine the properties of this model. Well, first of all, we can see that the solution exists and is unique up to the explosion time because everything is class C1 and is a homogeneous diffusion process with a drift coefficient equal to the deterministic part of the equation and the diffusion coefficient equal to the coefficient of the stochastic part of the equation squared. We can define the scale and the speed measures characterized by their densities and by their integrals, the scale and speed function. And now I remind you that f of x is the average natural growth rate, the arithmetic average natural growth rate, okay? But since this is a multiplicative process, we really prefer to, it's better to use the geometric average natural growth rate, which is the arithmetic average with the correction term. That's the natural growth rate. But since we are harvesting, we are interested in the net growth rate. That is the difference between the natural growth rate and the mortality rate caused by fishing. So that's the net growth rate in geometric average, okay? And now, what can we conclude? With the very general assumptions we have made, and I'm talking about cases in which Allee effects are not present, okay, the solution exists and is unique up to for all times because we can show that the infinite boundary is not attractive, which amounts to show that the scale function at infinite is infinite. And this implies that there is no explosion, so the solution exists all the time. Now let's look at the extinction boundary. Let's look at the geometric average net growth rate when the population size is small. In that case, if this is negative, that is, if the fishing mortality rate is higher than the natural growth rate of the population in geometric average, then we are overfishing and mathematical extinction will occur with probability 1. By mathematical extinction, we mean population size going to 0. To show that, we just have to show that the zero boundary is attractive, which is equivalent to showing that. That implies almost sure extinction. On the contrary, if when the population size is small, we have a net growth rate on average positive, that is, if the mortality fishing rate is smaller than the natural growth rate of the fish in geometric average, then we have sustainable harvesting. Mathematical extinction has zero probability of occurring, and the process is ergodic, and there is a stochastic equilibrium, in the sense, not in the sense that the population size converges to an equilibrium point, but rather that the distribution of population sizes converges to an equilibrium distribution as time goes to infinity. And that equilibrium distribution has a stationary probability density function, the stationary density P of x, which is proportional to the speed density. To show that, we have to show that the boundary is non-attractive, which is equivalent to that. And of course, we have to show that speed measure of the state space is finite, so we can normalize the speed density. Now, of course, that's mathematical extinction cannot occur. But even in this case, a population of, say, 0.4 individuals, is it extinct or not? Of course, it is extinct, but not mathematically. So we should put as extinction threshold a small positive number, and the population reaches it, we say it's extinct in realistic sense. But realistic extinction will occur in every case, because even in this case, the process is ergodic, so it will cross that the extinction threshold. The question is, how long does it take? If it takes longer than the lifetime of the universe, then we don't worry. But if it occurs for some parameter values, for other parameter values, though, the extinction can be quite fast, a few generations, and then we have to worry, and we have to determine mean and standard deviations of extinction times. Well, now let's assume now population has Allee effects. What happens? What are the conclusions? Strangely enough, are exactly the same. The solution exists and is unique. If the net growth rate is negative, we have extinction. If it's positive, we have an stochastic equilibrium. Okay, exactly the same conclusion. So what is different then when we have Allee effects? Well, the difference is that with Allee effects, for low population sizes, the net growth rate gets depressed. And sustainability, that is existence of an equilibrium, requires we exert a smaller fishing effort. It also affects the choice of the best harvesting policies. It's different from the case where there are no Allee effects. And realistic extinction occurs faster, much faster than without Allee effects. Now, let's look at the economical situation. We have a profit per unit time. pi t, which is the difference between the sale price per unit time and the cost of fishing per unit time. The sale price of fish per unit time is going to be equal to the yield, that is the amount of fish we catch per unit time, multiplied by price per kilo, which is usually is assumed to be constant, but we allow it to go a little bit down because of competition in the markets. Then the cost of fishing is assumed to be proportional to the fishing effort, but we usually it's assumed constant, but we allow it to go a little bit up because we may have to resort to less efficient vessels or pay overtime to fishermen. Now, what we want to maximize is the profit. Actually, the expected accumulated profit over some time horizon, 0 capital T, with the discount rate delta, which takes into account the loss of opportunity of investing the money somewhere else or other social discount rates. This is just the function J computed at time 0, J being the remaining profit at time T. Now, how we obtain that? Using a stochastic control theory. We want to determine at each time T what is the effort E star of T that maximizes the present value, subject, of course, to the growth condition, the growth dynamics of the population, some restrictions on maximum and minimum values, and also a terminal condition for the function J. The solution is obtained by solving the Milton-Jacobi-Bellman equation, which we usually do by numerical methods, and this is given by E star free, which is if we don't have any bounds on the effort, but if we do, we have to restrain the E star. Okay. So we have the solution. Okay. Now, we thought, but this solution has many drawbacks, as you will see. So we thought of an alternative, much simpler to apply. Let's assume the effort is always the same number of vessels, same number of days fishing, irrespective of the population size and time. Well, the cost and profit structure is exactly the same, except now we know that with the constant effort, and if we're not overfishing, sorry, 5 minutes? Oh, okay, but fast, well, the fishing effort is, so if we're not overfishing, then we know there is an equilibrium of proper distribution, and we're going now trying to determine what is the constant effort that maximizes the expected sustainable profit at equilibrium, profit per unit time at equilibrium. Okay, the cost structure is just the same, except that we compute things at equilibrium. And we apply that to the Pacific Halibut data taken from Hansen. The data, the values are here for 50-year horizon. And we've made the 1,000 simulations. That's for the optimal control theory solution, and that's for the constant effort. Okay? And you can see that's a trajectory. One of the 1,000 trajectories shows it at random. Okay, that's what typically fishermen will feel. That's the average of the 1,000 trajectories, which is basically the expected value. And you can see, looking at the effort, that with the optimal control theory variable effort, we have a highly variable effort, changing all the time, and that is not possible to apply in practice. Furthermore, to determine the optimal effort at each time, we need to estimate the population size, which is not possible to do it every time. So this is not feasible. Furthermore, we have periods of zero profit or very low profit with an unemployment of fishermen, which may give rise to hidden costs, but especially has some social problems. With a constant effort, no problems, no social problems, no difficulties implementing because the effort is always the same. Look at the profit. On the average, the profit per unit time is better here than here. But the profit, the actual profit the fisherman sees varies quite a lot, while here it only varies a little bit. Now, we thought of intermediate policies in which we use the optimal policy, the one that's not applicable, but you've determined the effort, the optimal effort at the beginning of a period of 1 year, and freeze it for that year. So we have a stepwise effort, or for periods of 2 years, if you prefer. So we have similar things, but now it's applicable because you change the effort only once a year, and you determine the population size only once a year, although we still have the social problems. Okay. Now, we applied that also to Bangladesh shrimp. We're using the Gompertz model, data from CAR. That's the data which the results are pretty much similar, so I not spend time just showing the final result for the two. That's the present value using the optimal policy. That's what the present values are using the optimal policy. That's using the stepwise policies, the ones that are applicable contrary to that one, but still have social problems, and the constant effort policy, which is very nice to apply and has no social problems. Notice that you only lose 4%, so not that much by using a very nice policy. In this case of the butterless shrimp, you only lose 1.5%. Okay, now let's see what happens if we have Ali effects. That's the optimal variable effort policy, the one it's not applicable, but a similar thing applies to the others. We have a logistic model without Ali effects, and then we have Ali effects. Weak Ali effects, because strong Ali effects lead to extinction, okay? Weak Ali effects, but mild ones and more intense ones. Notice that average effort. Well, the problems are similar, of course. So, the social problems and all that are similar, but notice the average effort, expected effort. The expected effort is smaller and smaller even here. And the expected profit's even smaller. So with all the effects, we reduce have to reduce the effort, and we have to reduce the profit. The more so, the more intense are the other effects. But we can compare this in this slide. If you compare, for example, for this policy, the variable effort policy, the optimal one, which is not applicable, but the same reasoning applies to the others. If you have all the effects, the profit is much lower than this one, okay? 28% lower. And if you have more intense Ali effects, it's even worse. We lose 47%. Now, if you want to compare which policy you should use, well, in this case, you could use this one or this one, stepwise, or the constant effort, because you only lose a few percent compared to the optimal inapplicable policy. But here, be careful, because here, well, one stepwise 1 year, okay, but constant effort, you lose 11%, and in this more intense case, you lose 62%. So you cannot apply the constant effort policy. So basically, just to make conclusions faster, I would say that for a good choice of the harvesting policy, one should not blindly apply the traditional models with no Ali, assuming there are no Ali effects. We should check if there are Ali effects, and if there are, how intense they are, and that will help us in choosing the best policy to apply in fishing. Okay, that's about just some references. That's the cover of my recent book. More references, and gracias, obrigado, and also thank you to our sponsors of this research. And thank you.
Now, in the beginning of the conference, we will have some time for questions. If we continue, Salo, sim, dizendo.
Professor, tenho que deixar de partilhar a tela para eu poder partilhar.
Tá bom. Ótimo. Obrigado.
Obrigado, professor.
We're going to present
Okay.
individual role model with discussing the differential issue.
Estão a ver os slides? Está tudo ok?
Sim.
Sim, ok. Hello, everyone. Thank you for this nice meeting. My name is Gonçalo Jacinto. This is a joint work with my colleagues, Professor Patrícia Filipe and Carlos Brauman, and our PhD student, Nelson Jamba. We'll present our main results about individual growth models using stochastic differential equations. And in this case, we are going to apply it to the weight of bovine animals. This work was developed under the GoBovMais project. This project has the participation of University of Évora, with several research centers and several animal associations. And we have data from males of Myrtle cattle breed and also from Lentiana cattle breed. And this association, a CBM, is an association that enables breeders to breed and finish their cattle when they don't have conditions for that. And by doing so, they obtain a higher economic value than is normally achieved by the farmers. Usually, the classic regression model is the usual model that is used in individual growth models. The problem is that it is very unrealistic when the deviations are due to random changes on the growth rate induced by environmental random fluctuations. So, for instance, if in a regression model if a delay occurs at a certain time for a given animal in the growth, that delay has no implications on the future weight of the animal. So the prediction is based on the average curve. On the other hand, the stochastic differential equations does not have that shortcomings. They are built precisely to incorporate the dynamics of the growth process and the effect of the environmental random fluctuations on such dynamics. And so predictions are based on the actual size of the animal. The classical regression model usually models the individual size XT of a given animal. This size can be the weight, the height, or the length of the animal of a given HT. And is given by this stochastic differential equation, where here we are going to use the modified size, YT. This is modified by a function h, which is strictly increasing continuous differential function. And this choice of h enables us to model different non-classical models in this same framework. So you have to use this setup. Now the coefficients are beta. The coefficient beta it is the growth coefficient that measures represents approximation rate to maturity. The parameter alpha, that in fact is the modified asymptotical size, or the size at maturity of the animal, and the parameter sigma, that is the environmental noise intensity parameter. This model is also known as a variant of the Ullstein-Uhlenbeck model, and is usually called also the Vasisek model. It has a very known solution. It is by a homogeneous diffusion process with this drift coefficient and this diffusion coefficient. The drift coefficient is the mean speed of growth described by the modified weight size. And the diffusion coefficient measures the local magnitudes of the fluctuations. And it has a explicit solution given by this expression, which can be proven that it has a normal distribution with this mean and this variance. Well, we have data from 6,029 Mertelingo cattle males. It is a very heterogeneous database, since you have animals with only 3 observations of weights and animals with 33 observations. Their ages are ages that vary since birth until 0.2 years old or 16 years old, so it's quite heterogeneous. And during this project, and because the original data has not enough animals at higher ages, which enable us to accurately estimate the growth curve, and especially to estimate accurately the weight of the animal at maturity, the parameter alpha. We also create this test group. And this test group has companion animals weighted every month, 18 animals weighted every month until 24 months of age. And so this test group, we have very nice curves, which you have all the weights every month. And we also can see the approximation of the weight of the animal at maturity. We are working, we tested several models, but we finally reached to the final 2 models, the stochastic Gompert models that use this function h, and the stochastic Bertalanffy models that use this function h. It was the best models to fit to our data. And we use the maximum likelihood simulation theory, the classical one, with the asymptotic confidence interval obtained through the empirical Fisher information metrics. And comparing these 2 models, at the end, we believe that the stochastic Gompert model was the one that suits better to our data, and it was the one that you use it most. Okay, so I don't have enough time to explain all the results that we have done during this project, so I will summarize in 3 different topics. Basically, the first one is the profit optimization, where we have obtained the optimal selling age and weight of the animals. Then we are going to improve the estimation methods using a weight maximum likelihood method. And finally, the one that you are still working in is the mixed models, where we allow that the parameters alpha and beta, instead to be fixed, they vary randomly from animal to animal, in order that we can include the individual characteristics of the animal, especially the genetic values of each animal. Okay, let's jump to the profit optimization. First, the problem we want to obtain the expected value and the variance of the profit of raising an animal since an HT0 until the HT, where he is going to be sold to the meat market. Notice that before HT0, it could have any some costs that you not considered in this model. Okay, so it should add it if there is any costs. But the profit LT is a function of the age of the animal and also of the weight of the animal at that age. And is the difference between the income, the selling price of the animal, and the raising costs that the association had until raising the animal to HT. So regarding the income, selling price, we notice that the selling price, PT60, depends on the animal's age, T, and the carcass weight, the category. The carcass weight, RXT, is in fact the relative weight of this live weight regarding to the carcass weight. So we should have the dressing proportion R, that is a percentage of the live weight of the animal that are selling for the meat market. So since the price table of the association is quite complex, they have several prices depending of if the animal is younger, or if the animal is older, several prices considering the weight of the animal. We should consider that the carcass weight into consecutive no overlapping intervals in order to consider the different price categories, and so the price, the selling price should be written in this form. Okay, and regarding the raising costs, the raising costs are divided in three types of costs: the fixed costs, the taxes, sanitation, transportation; the maintenance cost that only depends of the time that the animal spends in the association; and the feeding costs that depends not only of the time that the animal spends in the association, but also the amount of food that the animal eats every time that is where the weight is evolving. Okay, so the profit is written in this expression, where we have here a complicated stochastic interval to solve when you need to obtain the expectation value of the profit and the variance of the profit. For the expectations, we just need to obtain truncated moments of the non-Gaussian weight process XT, but for the variance of the profit, we need to obtain also the covariance, and then it involves quite hardest equations for the truncated autocovariances. So the final objective of this first problem was to develop formulas, simple formulas, that the association, and especially Ruralbit, that is the company that supports them informatically, can apply these results in the software in order to the farmers at any time can input their costs to a given animal and the weights of the animal long time, and then the software reports the optimal selling time and the optimal weight to improve their profits. So to implement these equations there is quite difficult, and also we observe that it is usually not possible to obtain the feeding costs per unit time. So the farmers most of the time only know what are the mean feeding costs per unit time. So they gave a bunch of food to the animals, and then they know that a certain number of animals eat all that food. So a simplified assumption, and the needed one, is to consider that the feeding costs just vary by unit time. And then this stochastic integral here will be simplified, since we can join here the maintenance cost with the feeding costs, simplifying all the expressions and all the calculations of the expectation and the variance of the profit. So just to compare if this simplification provides very good approximation, you can see here at black the curve of the raising costs. And you can see here the raising costs with the most complex approach. You can see that for the optimal selling age of the animals around this time, the two curves are very, very closer. So we can conclude that this approximation fits very well if we are selling the animal at their typical age. Of course, if they use this application for to obtain the optimal selling age for an older animal, they should consider the more complex approach. Okay, I will pass here all these mathematical developments. So the final result is basically what the farmers see in the application is that they will see what is the optimal selling time and the expected profit by selling the animal at that optimal selling time. We compare it with the usual selling time of the association, and we can see that the association is selling the animals around 1 month and 2 weeks earlier than they should be in order to maximize the profit in around 6 to 7%. Okay, the results and the details are in this paper, and I'm going to pass for the second topic. The estimation is weighted maximum likelihood, and the problem here is different. We know that all these animals have observations that are not equally spaced, and they have a small number of observations at higher ages. Instead, the 18 animals of the test group have a very steady curves and very good values here in the higher ages. So what we thought was, if we introduce here a weight in the maximum likelihood function, in order to that weight gives more leverage to observations at higher ages, or more leverage to observations that have a higher space between them, maybe we could improve the estimation of the parameters. So after several tests, we reached this result, where we can see here that we are measuring the function of two consecutive instances of the animals, of the weights of the animals, by a non-decreasing function lambda, which takes into account this time elapsed. And this function also are taken more leverage to higher ages than higher interval between observations, and we consider this formula for this function for this lambda t. So we're interested especially in the effect of this power w in the estimates of the weighted maximum likelihood. And if it is interesting that if this power w that maximizes the quality of the estimators is in fact w equal to 1, we conclude that in fact the classical maximum likelihood method is the best one to estimate the parameters. So we compared constructed several databases to compare higher ages versus smaller ages, etc. And we obtained the optimal value W that minimizes the statistic that is error measurement of these estimates. Basically, is the mean relative error of the estimates. And basically, the results said to us that if you have a database with higher ages, the error is lower. If you have a database with a gap between observations lower, then the estimation is lower. And this is very interesting to note also that for these data sets where we have constant observations, 15 to 50 days or 40 to 40 days, the classical maximum likelihood method is the best one. Okay. That does not happen when you consider the real age scheme. Here, the parameter lambda w is far away from the one of the classical maximum likelihood. And if we compare the two methods of estimation for the realistic age scheme age, we can see that the error of the weight maximum likelihood is much lower than the error of the maximum likelihood method. Okay, which tell us that this weight maximum likelihood in this type of data, very heterogeneous, is the best method to estimate the parameters. I need to go forward for the last 2 minutes. So finally, we are working now in the mixed models. The interesting part here is that we want to incorporate individual characteristics of the animal, especially the genetic values of the animals, in the parameters that before were fixed, alpha and beta, the size at maturity and the growth coefficient of the animals. So for that, we consider that the parameters vary randomly from animal to animal, which give us mixed models, stochastic differential equation mixed models. So this topic should be very fast. Instead, we reached to a time where we observe that the package available in all literature, in the HARF especially, does not allow to consider animals without equal spacing of time and without the same time vector. So we were forced to develop our own method to estimate this case where the alpha and beta can be random. For a single case of a unique parameter random is alpha, we already have this closed format developed in the PhD thesis of Professor Patricia Flipp. But for the case of beta random, or the case where both parameters are random, we do not have any result that could obtain our estimates for our real data set. So very quickly, we have here our stochastic differential equations. Now beta I and alpha I depends of the value for each animal, and you assume that they have a normal distribution of these parameters. So we have a random effects parameter given by the parameters of the normal distributions of these two parameters, and the fixed effects, that is sigma. By conditioning on the distributions of alpha and beta, we reach to this likelihood function that is very simple to write. Is the expectation of a function y that depends of each animal, which is the exponential function of gy, which is given by this expression. And then by expansion in the second order Taylor series around the point, the mean point of the normal distribution of the both parameters, you reach to this approximation of this expectation, and then to this approximation of this log likelihood function. So our proposal method, our delta method, reach to a closed form expression. We have closed forms for each of these functions, but they are quite ugly, but they are closed ones for the log likelihood function. And then we compare the results of the existing package that consider data sets with animals' weights measured at the same ages with our method, our approximation method of the log likelihood, both when both parameters are random, just one of them are random, or none of them are random. And we conclude a very interesting thing. We conclude that in the case that both parameters in the preliminary analysis can be assumed fixed, we should use the classical maximum likelihood method to estimate the parameters. If we conclude that just the parameter random alpha is random, then the exact method already developed, which we have a closed form, should be used. In all other cases, our approximation method beats all other methods that are used in the literature. It's the best one that gives the best estimates. And finally, to the last slide, for the real data set, we compared our estimates with the assumption that we had before that the parameters are fixed, and we conclude that in this case, we should not consider the parameters fixed, but random. They improve the estimation. The results are here, and thank you very much. Sorry for the delay.
Now, we continue with Professor Ligia Enriquez Rodriguez. Ligia, you there?
Yes, I'm here. Can you
Okay.
hear me?
It's okay. The figure on the presentation is a contribution in the semi-parametric estimation of parameters of the fleet analysis. Please use.
I'll try to share my screen. Okay. Can you see my slides?
Yes.
Yes? Okay, so good afternoon to the colleagues in Costa Rica. Good morning to the colleagues in Costa Rica and good afternoon to the colleagues in Portugal. I'm trying to, okay. So I'd like to thank the organizers for putting together this workshop, joining these two research centers. I'm going to talk briefly about some contributions in the semi-parametric estimation of parameters of extreme events. So I'll start by providing the theoretical framework to work with extreme events. In our case, I'm interested in working with maximum, but the results can be easily extended if we want to work with minimums. Okay, next, since I'm going to address the semi-parametric estimation, I'm going to provide some of the main results in order to assure that our estimators, they are consistent and that they have asymptotic normal behavior. And I will present the yield estimator, that is one of the most known estimators when we work in extreme value theory. And this yield estimator has some properties that led the researchers to find and to try to reduce bias. And I'm going to present two contributions that are related with this topic. So the two contributions are this one that I'm going to talk ahead. So let's start by presenting that we are working with a random sample of NIID random variables. These random variables can be stationary, weakly dependent, and they have a distribution function, capital F. I'm going to denote the order statistics by this. So x1 of n will be our minimum, xn of n will be our maximum. So the main theorem in extreme value theory is the extreme types theorem that establishes the asymptotic behavior of the maximum or the minimum. I have here the version for the maximum. So what we know is that if we can find constants an and bn such that the distribution of the maximum linearly normalized converges to a non-generate random variable, the distribution function of this random variable must be of a generalized extreme value distribution type. So this is the functional form of the GAV distribution, generalized extreme value distribution. When this convergence holds, we say that F is in the max domain of attraction of an EV psi. And we use this notation to denote this. Psi is our main parameter, is the extreme value index or the tail index. And essentially what it's doing here is a shape parameter is measuring the weight of the tail. So the larger psi is, the heavier the tail is. I have here a figure where I have three different values of psi, and I have aquí the PDFs, and I have also the standard normal PDF. And on the upper right corner, I have a zoom of the tails just to see and to compare the weight of the tails according to psi. So on the green line, we have a positive psi, the black line, we have psi equals to 0, and the red line, psi, a negative psi. And the dashed line corresponds to the normal distribution. So we can see that when psi is positive, we say that our model is a heavy tail model that belongs to the Frechet domain of attraction. The tail is of a negative polynomial type, and the right-hand point is infinite. If psi is 0, this is the black line here, we are in the Gumbel domain of attraction. Our tail is of an exponential type, and the right-hand point can be finite or infinite. If psi is negative, as you can see here, the right-hand point is finite, and our tail is light. Okay, so we have here an example. So when I address the semi-parametric estimation, I have some notation that we use. So I'm going to denote by this the generalized inverse function of f, by u of t the quantile function, and we are going to use the theory of the regular varying functions that I'm going to denote here by RV alpha. And essentially, they are positive measurable functions that satisfy this type of condition. So in what I'm going to present, I will only work with positive psi. So I will work with heavy tail models that are in the Frechet domain of attraction, or with tails of Pareto type tails. So for this type of models, we have several conditions to allow us to guarantee the nice properties of our estimators. The first one was proposed by Lawrence Dian in 1984, and it is a condition that allows us to guarantee that our estimators, they are consistent to the estimation of psi. This condition is not, needs another condition that establish how many k top of order statistics I'm going to use in the estimation of the extreme value index psi. And so I have to assume that k is a sequence of positive integers that goes to infinity, but at a smaller rate than n. So k over n goes to 0 as n goes to infinity. So with these two conditions, I have consistency. In order to derive the asymptotic behavior, I need to impose another condition, ruling the rate of convergence on the first order condition. This rate of convergence is ruled by this parameter, this shape parameter rho here. And this A function, as you are going to see, plays an important role when we address the bias reduction of our estimators. So for technical simplicity, and as this function A plays an important role, we need to have a parameterization for this function. So we are going to assume that we are working in a vast class of models that contains almost all heavy tail models. This class is called All-in-Welsh class of models, and the quantile function can be parameterized in this way. So we have a nice parameterization for our A function. There appears here a new parameter. This is beta, that is a scale second order parameter. Okay, so regarding the classic estimators of our tail index, the classic estimator, as I said in the beginning of this talk, is the yield estimator. Is very simple because it's just an average. Okay, so it's an average of, we can do two average. You can make an average of these quantities here that are called the log excesses, or it is an average of the logs of scale log spacing. So we write according to what we want to do. As I said, E is consistent, assuming first order condition, and that K is intimate. And in order to guarantee the asymptotic normal behavior, we have to impose a second order condition. So we have here the asymptotic representation. And when we look to this representation, we have some problems here with the estimator. So the first problem with this estimator is when K is small, we have a high variance. And when K is large, we have high bias. So we have the usual trade-off between bias and variance. As you're going to see, I will go show later, we have a low stability of the sample paths. The mean square error is very peaked, so it's not easy to choose the number of K top order statistics. So researchers in extreme value theory have tried to improve the estimator, and they have proposed second order reduced bias estimator. So I've been working this since my PhD. There are several ways of doing that. In my PhD, I study the behavior of the log excesses of the scale log spacings of the second order behavior in order to reduce bias. The easiest way is to try to estimate the dominant component of the bias and remove it from the estimator. And today I'm going to present two more contributions. One that is related to the fact that the estimator is an average, so can think of generalized means and try to improve the estimator and reduce bias. And another contribution was the use of a box-Coq transformation of the order statistics in order to reduce bias. So let's start with the first work. This is a joint work with Marie-Yvette Gomes and Inês Pestana. Yvette Gomes was my PhD supervisor. So what the beginning of this work was to see that the yield estimator is an average. And if we write it properly, we can see that the estimator is the logarithm of the geometric mean, or the mean of order P, the mean of order 0, sorry. So my colleagues, Fatima Brilhante and co-authors, they generalize this concept of mean of order, and they propose estimators, a class of the AV estimator that was the mean of order P. This is the functional form, generalizes the estimator. It's quite flexible since we have this tuning parameter P, so we can choose it properly in order to reduce the bias, and they have nice properties. And they proved that the estimator is consistent for values of P smaller than 1 over xi, and they proved also an asymptotic normal behavior for values of P smaller than 1 over 2 xi. So the main work that we did was to find and to try to understand what was the asymptotic behavior of this class of estimators for values of P between 1 over 2 xi and 1 over xi. Okay, so this problem is new in the sense that we cannot use regular frameworks to solve it. And we had to move to and work with a non-regular framework. So we came back to the beginning and we studied the additive stable laws. I have here the result, one of the main results of the additive stable laws that says that if there are normalizing constants such that the sum of a sequence of IID, the random variables, converges in distribution to a non-degenerate random variable, such random variable must be an additive stable law. Okay, and we denote by this the additive stable law. Alpha is the characteristic exponent, and beta is another parameter. So these stable laws, they have many drawbacks because we only know the density in 3 cases: the Levy one, the Cauchy, and the normal. Nevertheless, we try to use it in our work. So if this result holds, okay, the distribution function that is common to all these random variables satisfy this kind of property using the generalized central limit theorem. So we have that this is a regular varying function with index minus alpha, and that these converge to 1 minus beta over 2. So the question was, we are going to apply to our estimator, but where do we start? So I have here a remark for those who don't work with the order statistics. And these are xi of n are the order statistics associated with the distribution function capital F. And we know that these order statistics are equally distributed to the quantile function applied in other order statistics y I of n, where these order statistics, they came from a Pareto standard, a unit Pareto random variable. So we are going to start to study the standard or the unit Pareto random variables. And our first result was to prove that if y is a unit Pareto random variable, y to the power xi belongs to the additive domain of attraction of a stable law with beta equals to 1 and with a characteristic exponent given by this quantity. So taking this in consideration, we have to prove this result that was not so easy to prove. That was the average of these statistics here. So we have proved the behavior of this average for several cases of psi, and this allows us to establish the, sorry?
a minute.
Okay, we were able to establish the behavior, the syntactic behavior for this region. That I have here, I'm not going to enter the detail. This is as far as we know, the first work where we worked in a non-regular framework. So our second and last contribution, I'm going to be brief in this case, was to apply a Box-Cox transformation to our order statistics. Box-Cox transformations are very widely used in statistics, so why not use in extreme value theory was our idea. Maybe you can reduce bias. So we took the findings of this work by Tegels and Varol in 2004, where they study the applying when we apply a Box-Cox transformation, what are the effects on the first and second order conditions. So we took his findings and they showed that the velocity of the second order condition could be increased if the power transformation of the Box-Cox, the power is chosen by this way. So what we did develop the Box-Cox estimator that has this functional form here, depends on this power and shift. We have a power and a shift, and is obviously a generalization of the estimator. Just take A equals to 0 and sigma equals to 1, and we have the estimator. And what we did was to derive the asymptotic behavior to study is finite sample behavior. So we have here the asymptotic behavior. The nice property is that we can have a reduced by estimator by choosing A equals to B times C to the power sigma. And that was one of the main results. Then I just have here some of the Evitel models that were used in the simulation study. I have here the parameters. What we did that I'm not going to show here, we have estimated the A parameter and sigma parameter that appears in the Box-Cox estimator. And I'm going to show here just to finish a graph, just a graph, where on the left we have the mean values, on the right we have the mean square errors for a birth parent based on a sample of size 1000 with 1000 ranks. So the black line is the estimator. As I told you before, I variance for small values of K, I bias for large values of K. This magenta line is another reduced by estimator that I didn't talk today, but we use it to compare the performance. So we have here a yellow, orange line. This is our estimator, assuming that we know all sigma and A, the parameters are all known. So this is great, very stability and low mean square error. And the blue line is the one that really matters, is when we estimate properly the parameters of the Box-Cox estimator. So we have here a nice stability for sample pass, a small bias, and smaller and a value of mean square error that is minimum and has a lot of stability. So these are the two works that provided these findings. And thank you for your attention. And that's all. Thank you.
Thank you very much. Okay, next speaker will be Mario Villalobos, who is going to be talking about curve fitting for pandemic data using generalized logistic regressions. Okay, we start. Ready? Okay, thank you for give me an opportunity to present my work and welcome to SEMA people, because I expected there will be the first and not the last, and I will hope to stay particularly. Okay, I'm going to talk about the feeding the pandemic data, but you use this to estimate the data in the pandemic, like, so this work we start in the first days of the pandemic, when I was in my house, I had to find something, I find us and give me very good results. Okay, this is a work with the COVID group from Costa Rica. We are a group of people from pharmacy, biology, communication is very interesting because usually in mathematics you don't think about to have a person of communication to make a very good communication about computing, statistics, and mathematics. There are very good big group, and we're trying to continue working with this. Okay, this the idea was that this is the classical curve of the population growth. This was the data from China in the first day of the first 80 days of the pandemic, and this was the data in the cases in Costa Rica, the first days. Okay, and we see this is another disease, for example, then the cases for week in Costa Rica, and the other is very interesting because this was the idea is that survivors survivors, people in the country, they very useful in social science statistics because it's the same function. Now in this case is decreasing. Okay, we know that this is the curve. Okay, this is the equation, but it's too. The problem with this curve is too. This is the curve. The solution is perform the data and then using linear regression. But the problem with this is, you see, we have problems with the physics not so good. Okay, but it will be not so bad. And the problem is the value will be scalar to the interval 0.1. Okay. And what happened with the classical models? The classical models, as Fabio talked today, this is some parameters, but well, this is the classical models, right? The classical rho 0, rho d, and the SER models. Okay, but the problem with this models are the parameters. Fabio talked about that not easy. You have to see in the very first day, so that when they make you have very little data, and then it will be very difficult to obtain the parameter with the data. And as Fabio talked, now there's something to change these parameters with parameters depending on the time or the moment of the pandemic that will be. Okay, but this I try to use the first proposal. This was this curve, and with that make a more complex function. I have to tell you that I think about the model when I'm working with survivor group. And the idea of the alpha is the effect with a potential function. You know, that with this using this alpha data, we made that curve more flexible. Okay, and then we see. Okay, but when I was studying the models, I found that this model is a particular case of this. Almost the same, only this is the difference. That is the model, is the Richards curve that was used to grow population growth. He used it in I don't know it's on disease. Okay, but and this is the solution of this equation. Now it's similar to the professor presenting the first talk today. Okay, and okay, and the more simple version of this curve is the Gomper function. Okay, in the first time I was using this, And now I use it the other. Here are 3 parameters, and the other in this other there are 4 parameters and minimum threshold. Okay, and when I found in the first data, I try to use in some moment a legal trend, because in some cases I suppose that some diseases will stay in for that some time. Okay. Or this is the version, the legal trend version for the content function. Okay. Oh, I was thinking to use a more complex that will be some. This I used this model in the survival field. And why I use this? Because when I come for the data, when I use it, I come for the data to apply the physics. When I come for the data, I saw the curve is not aligned. It's that. And I then very good results to fit in the text. Okay, in the case, I use minimum. And detail is the data, and each data is the piece. Okay. The very interesting this problem I solve using a solver because it's a low type. And the other idea is when I have an optimal for today, and I add one more data, the new optimal will be very close to the previous. They will be very different. Okay. Okay. I have to help solver because it's not just put a solver. It's not the first time it's not so good. I had to make some try to make some variation and some rotation of the parameters. Okay. With this, what I want the hypothesis and the proposal. The hypothesis was if you use the cube or buffers to make a figure of the data, it will be very easy. It will be very easy. And the second is we have the lower part of the cube, okay, the initial data, 30 days, and we know that the size, the front of the cube, we can obtain all the cube. And was very okay. Obviously, in the pure fitting, this is the data of China that days. In that days, one day was 50,000 cases, and I correct the data, and you remember the first data. The fit is very good. Okay, but it will be home. Okay, and this is the data for South Korea at that moment. And we saw here the alignment trend. And in this case, I use this function, and this is the fit is very good. Obviously, the next data will change, and this. How about the trend? The trend of the results. This is the data from Costa Rica. In this moment, we have about less than 30 days. And we can estimate the data for 10 days, 100 days. And this was the first whole period. When in Costa Rica, and the data was really good. In that moment, it's about 800 cases, and the tool was very good. Okay, this is the Mexican case. This is the data from Mexico. This is the tool that I fit. And this group was made in August 14 in 2020. Okay, and the data, the fit in 45 days later. Okay, this is the fit, and this is the data in kilometers. This is the kilometers, and we can see that it's very good. Okay, and you can see in the data, I feed that, and I obtain the orange line, just taking the rest of the next day, 2 days. Okay, and we can see here start the next way. Because of that, the big dog, okay. And this is the cases for Costa Rica. That's for me is very impressive, very good, because I obtained the red line with the data about September 19. Okay, and this data will be until March 6 months. And here I give the data go 5%, but this will be effect on I know a small weight that you're giving in the few months of 2022. Okay, and for me it was very impressive because 6 months. I put the data and the data stay in the. This is the data from Salvador. And at this moment, we have problems, but we have to obtain the linear trend will be some correction, but not too good. And we have to think about the second or more waves. Okay, what the idea here? The proposal is to use a familiar function of this data. And take a sum of the with the data like this. Okay. We have the idea here, okay, this is the parameters, and the idea, oh, it will be the same in corporate. I using logistic, and this is the result for the data from Salvador. Okay, I will use it. Okay, this is Salvador from, and this is 1 years ago, almost. And we can see here the three curves, because this will be here the three curve, and the next curve approximate the difference. Okay, no, we can use here a group to fit. Okay, it's not so good because the data is not so good, but here in that moment, the world data, the first here are the small rate in China, like in China, and Guatemala, for example, with 6 waves. El Salvador, show you, Republic of Dominican Republic. This is the data, and we can see that the idea will fit in any cases. You can see there's a big wave here, and the function or the chain here is very data from Panama, Costa Rica, and in some time, this is the way I say happen. I call a because he started then disappeared. Okay, this is the data, but the data that I fit in the first score. Okay, and so someone told me, you do like this. I wrote, it's not some in this function. This is the actual data. We have a small wave at the end of the data. The next data is around here. Okay. And we have the data from Sonora, Mexico, and this will be the same. The thing is very good. And the idea of this is going to obtain the next wave. We are going to adding the next data. Okay, in the moment that we have 1, 2, 3 waves, we approximate the next. Okay, because we see it very good approximation. And this is the data from here. All the parameters, and we see that there are 4 parameters for 5 parameters because it's the key parameter for each wave. I mean, there will be a peak. And what about the other data? And the other data, this is and when we have the approximation, we try to obtain about the treatments, obtain, by example, hospital or UC issue people. Okay, but this is the real data, but the real data is the blue and the black here. But I try to using the data that the public administration gives, but it's not good. I tell some different that will be good, but not so good. Okay, and I decided to use the real active cases. Using the information that people say, okay, I said to you the real the data that is the public help. I try to use, I use 20 days for the daily reports. Okay, what I'm saying that the active cases will be the previous 20 days are report. When the data, we can found that this is the projection of the cases, and with that, I recalculate all the data and obtain very good. For example, this is very good in the variation image. And with that, I obtain this. We can see this is the real data, and the blue lines in this case is interval that can give you the data. What I say, I'm saying that with this data using this percentage, we can replace the number of people in the hospital, or the same in okay. This the data depend on the quantity of cases. If the quantity of cases is very big in the hill, it will vary. Okay, and this is a very interesting case because for instance, I calculate, and it fit in the weekend days. In the weekend days, already reported less cases, but this is the people, and this is the total dead people. You see, it's a very good estimation. Okay, another thing that we do, and in that moment, the trend will be that, and in Puerto Rico, you have to apply a hammer blow, all the people in the house, and this is the real data. Okay, you can see that the hammer blow had a good effect, and this is the same here, or the hammer blow. And other disease, data as shown the first. This is, I think, the data from 2019, and this is the. I think this will be similar to obtain this. The field will be always will be good, but the radio we have some days is we try to obtain it. Okay, there will be another nowadays another disease we can use. Okay, and in the other groups, I start in order work with the survivor group. Okay, and in this case, I had to use this polynomial square. Okay, conclusion, this method can be used as a trend of the population in case of the COVID or others. It obviously can help to spare some okay, other than as you see, I try to use it in many organizations. Refine the study of the result because I use the average of the 20 days, but it will be a linear combination of the 20. For example, for the hospital, okay. Other data, and use another software, but this I made this by hand, but it will be an idea to make software and make it. Thank you. Yes. Okay, now continue with the Rodriguez talk, and the title is Symbolic Listening and Cuba, method for interval value. Thank you very much. Good morning here in Costa Rica, good afternoon, Portugal. And thank you very much for seeing and thinking for this opportunity. Okay, well, I am going to talk about symbolic Disney and UMAP methods for interval value variables. The idea is to generalize this method to interval data matrix. The outline is I am going first to present classic Disney and UMAP examples. I am going to explain what is Disney, what is UMAP, and then I am going to explain symbolic UMAP for interval value observation. Disney and UMAP and the RDA's package. And at the end, I have written some preference. Okay, before explaining the theory behind Disney and UMAP, let's take a look at how this method performs in real data. For example, in IRIS data, very well known data. This is the execution of PCA, classic PCA. You can see how separate the Setosa, Pirsicolora, Quintinta. This is Disney. You can see the cluster separation is better. This is the UMAP in this data. It's also better than PCA. And another example, big example, handwritten BD data is a big example. Here we have a number, 28 pixel by 28 pixel. Zero is black and 255 is white. So in this case, we have this 3,784 dimensions of variable. It's an important problem for dimension reduction because we have a lot of variables. This is the execution of PCA. You can see in this data it's almost confused. This is thin, much better than PCA. And this is you. You can see it's much better. We have 100 years of evolution in the method. Well, what is Disney? This is a very new method. It was proposed by Lauren Martin of Tilburg University in 2008. And Disney comes from distributed stochastic neighbor embedding. And first step in the algorithm. The first step in Disney algorithm is to compute the distance between each case to every other case in the data set. I mean, compute the distance matrix. These distances are converted into probability. This is very important. We compute the distance between all the cases, and then we can form that in a probability distribution. And we can see the distance like probability distribution. So the idea is to have a matrix of probability that describes the distance, a matrix like this. Disney compute the distance between the cases in a new randomized low-dimensional space and convert them into probabilities, just like before. The only difference is that instead of use normal distribution, we use the T-student distribution. The idea is to compare these two distributions. Why, in this case, we use T-distribution? Also a question. This is because without it, the cluster would be all jump. And in the middle, it will be harder to visualize and interpret. The second step of the algorithm, this is the more important one, is make sure the data points around this new axis, step by step, to make the matrix of probabilities in lower dimension space look as close as possible to the matrix of probabilities in the original high dimensional space. To do that, we use callback labor derivative. The idea is to shuffle the data, as you can see here, until these two matrices would be as close as possible. This is limitation. This has important limitation. It is computationally expensive. Its computation time is exponentially with the number of cases in the data set.
It's a big problem because the initial placement of the data on the new axis is random. The running Disney on the same data set repeatedly will give different results. Disney retains the local structure in the low dimension representation, but it doesn't retain the global structure. But we don't have the feature there. This means that distance between clusters often don't meet anywhere. Well, to improve Disney, Leland McLean from Fuller Institute in Canada proposed the UMAP method. Very new method, 2018. And it comes from Uniform Meaningful Approximation Projection. And UMAP algorithm is based on algebraic polymer, logical data analysis, and Riemann geometry. So the theoretical interpretation of this method is very hard to read. But UMAP is very competitive with this, also for visualization quality and for interpretation. How UMAP works? UMAP works in a very similar way to Disney, but UMAP finds distances in the space with many variables and try to reproduce this distance in a low dimensional space. This is similar to Disney, but UMAP does it very different. UMAP assumes that the data is distributed in a long manifold. What is a manifold? A manifold is a uniform n-dimensional geometric shape in which each point for the manifold there is a neighborhood around that point that looks like a flat in two-dimensional space. It's like here is the wall, we are here, we see a plane. But this is not a plane. It's the biggest explanation of what is a manifold. In this case, we will use simplicial complexes, 0 simplex, 1 simplex, 2 simplex, and 3 simplex. And we will model the data using sample size complexes. The base of the UMAP method is the NERD theorem, the point of the methods. What is the idea of this theorem? We will have a topological space X, and we will have a data space N. And the idea is that we can find a projection in this new space. So X and N are homotopically equivalent. That permits us to use all the tools in the topology and all the data line to explain our data. And we have a lot of important tools here that we can use here. This is the idea. For example, suppose that the original data is in 3 dimensions, that's in this case, and we want to project this data in 3 dimensions. You must extend a radius of this outwards from this point, connecting points with those values overlap. So we can create a simplicial complex using 0, 1, and 2 simplexes as point lines and values. How to choose the value? Very critical problem. Choosing the values is critical. Too small choice will lead to small isolated clusters, while too large a choice will connect everything together. You must overcome this limitation by choosing radius locally. Base this distance in each point use something similar that can needed neighbors. This is very important in UMAP. We use distance locally. It's a very new idea. And to do that, we have to use Riemann geometry. UMAP then makes fusing that by decreasing the likelihood of connection of the radius rows, like this. Finally, by stipulating that each point must be connected to at least its closest neighbor, UMAP ensures that local structure is preserved in balance with global structure. The goal is to find low-dimensional representation that has a topological structure similar as possible to the high-dimensional structure. Therefore, since both topological structures that really are connected share the same zero simplexes and will compare to probability vector by one simplexes. To do that, we use cross entropy. This is very important idea in UMAP method. Cross entropy is very nice in this case because this part of the equation guarantees that interclass inertia is minimum. And that part is the second term guarantees that interclass inertia is maximum. So in this case, we have the feature here. This is very important. For example, here we have the data in 3 dimensions, and we have different projections in 2 dimensions. Well, UMAP is considerably faster than Disney. UMAP is a deterministic algorithms. That is very important. That is giving a same input, it always gets the same out. That means that unlike Disney is a new individual can be projected onto the lower dimensional representation. That is important because in this case, UMAP can be used as a supervised method. UMAP presents both local and global changes. So we have to teach it. Well, what is our idea? To apply this to symbolic interval matrix. The idea is to apply this matrix like this, when we have intervals. There's a particular case in symbolic data. How to do a PCA. Well, the idea is to project all the points, all the corner, all the tops in the plane, and then to choose the minimum in the components and the maximums. The minimum and the maximum, so the projection of hyperrectangle will be a rectangle. The vertices UMAP method, the idea is to get to form this matrix, but the problem with this matrix is very big. This matrix will have this size m dot to m dot. For example, with them 1,000 cases and 12 features variable, we will have a matrix approximately by 4 million rows. This is small. So this is a big problem in this case. So this is the projection using classic vertices PCA in the Chino data set. This is the very well known data set in symbolic analysis. This is the Chino data. We have 8 cases and 4 variables. And this is the classic vertices projections, and this is vertices UMAP method. Look, this is the cluster are better, and the size of the rectangles are smaller. This is very important in symbolic data analysis, because when we have a big rectangle that's like L, the interpretation is not good. Basically, that says that L is whatever you want. So that's nothing. And so we have here a better representation. And in fact, if you know the data, you can realize that CA is different. And you must find this observation, but not the PCA. Well, the classical PCA, vertices PCA in 1997, Shokal Chakriya, Adame Shokal Chakriya had found a very, very important equation. She transformed the explanation problem in a linear one. And she had found this equation to compute the minimum and the maximum component. And it was published in this very well-known paper. Well, my problem now is, in my case, can I find an equation like this to my method UMAP, symbolic UMAP? The answer is it is impossible. Now I know that it's impossible because UMAP is not a linear method. if not doesn't express the component like a bigger combination, so this is impossible. Well, what can we do? We have found a solution, but an algorithm solution, but a local solution. We have found local solution in the neighborhoods and an algorithm solution. And we have modified the original algorithm of McLennan. These are the algorithm modified that we have found to improve the method in order to do it faster. I'm going to explain it in time. And finally, we can execute now the Disney and UMAP symbolic using our package RSDL. We can download the CRAN, it's in CRAN, and it's very easy to execute Disney and UMAP. Of course, these have a lot of parameters here, but here we are using the full parameters. And finally, some reference. Here are the papers, original papers. Lauren Martens, Pins, Disney, and UMAP. And this is very important paper. Symbolic record. Important. That's all. Thank you very much.
Now we have some kind of question for any of the we're not represented today. I don't know if someone have a question. Great, Ligia, a question for you. Yeah.
Yes,
Can you hear me?
barely.
I can.
Okay.
So, have you tried the multivariate case in the semi-parametric estimators?
No, the multivariate case, what I'm trying now and I'm studying now is to try to accommodate several predators and try to create tail index regression models. You can do it in the parametric way, in a semi-parametric way, and to accommodate several predictors in order to our response will be an extreme. Our predators can be bounded or unbounded, and we are trying to play this and to create a model. But thinking on regression, tail index regression models. Yes.
And how did you try the bias correction in the regression case?
The bias correction, sorry?
Yeah. How did you work the bias correction in the regression case?
There is no bias correction yet. We are trying to develop a new model, and then we are trying to remove the bias. But we haven't found any work in that area yet.
Okay. Thank you.
Thank you.
Another question? Another question?
I have a question for you, Mario. Hey, your model fits very well with data. What about the prediction? What happened if you use training?
I use this in real data. But for me, was very impressive because I made the first big web for Costa Rica data. I made I estimated a curve in SW in trabajo de las últimas. I found I estimated a cube in September and the curve free the data only March. This is empirical, obviously. I tried to make some analysis in the data. Okay, the physics will be okay. This is the first time, 20 data, I estimate 100. The first way, and this is the case for Mexico. Mexico, the red line was created August 40, and 45 days later, this was the big data. We use the data was over to very, very good worker. And this failed because it started anyway. Okay, but in Costa Rica, this is the Costa Rica data, and in Costa Rica, this will be a big wave. But remember, this will be a small wave over the other way, and this red line was calculated with the data from September 19, and that the data was 5% of the real until in March. For me, was very crazy, and this part that go 5%, as you see, was the what I call the joroba, like the Cebu. I don't know. This, but even with this data, we have 5% of the real. It's very, very, very good. And another data, what I say is that we can use this to say another way coming, or this way is going down. Because if the data go out of the real or the line, start a new. For example, in this is the last data. This is the last way, but in this data, in that moment, I saw that this data were out of the line, and I predict maybe days ago that we will start again. And in the other ways, this data, this curve was big here. I put 30 weeks data, and data. For me, for prediction is very, very good. But remember, this is based on the Richard's models. Okay, I start to thinking about the predicting, but there are around for the Richard's curve that uses to. Okay.
Question about the variance of the parameter estimates. Okay, if there was any difficulty in getting some of those estimates.
Yeah, I don't do something like that. I try to make something, but I need to have it. Because I made, you see in the when I talk in the other data, I try to make, I made a statistic about the data reported for the health service, and I try to make some, but this is about that data, not about the parameters. This is about to have to do.
The other question I have is for Mark. When you use the intervals, you just like you call those intervals like 1, 2, 3, or do you use the value of the minimum or maximum of the interval? When you're using symbolic data, right? How you deal with the interval? Is it it's an order variable, or is it
Yes, there is two approaches. One is to use the center and then the maximum. The maximum and minimum that are supplementary data. Another approach is the original one is to use the order minimum and maximum. And we assume that the original data follow the uniform distribution.
Okay, you know, I think it's not. The question
in chat? Is there any question in chat?
okay. Thank you very much. Thank you for the. we're going to make a break. Here, just to get back on time. At 10:20. Costa Rican time. 16:20 Portuguese time. And for the percentages, remember to keep track of the time. So thank you. Now, Roman, you have a question?
No, no, I just say goodbye. That's still. See you in a few minutes. See you in a few minutes.
Bye-bye.
Hello, everyone. This is our last session. These last 3 days. And we will have Michael Solis, who's going to be talking on geometric goodness of fixed measures to detect factors in data point cloud. Thank you very much. And thank you. Good morning. Thank you, Bert, to the organizers, INPA, IMA, and Mora University for having this excellent work. Well, this work is done with my colleague Alberto Hernandez and Edgar Hernandez, my student. And I want to present some good a new index of goodness of fits, different with the R squared that you already know. So maybe I want to start with some motivation about the problem. In statistics, it's a common task to recognize and measure patterns. In fact, if you recognize these patterns, we can detect a variable is important or not, the noisy or not. And in this case, we can make some dimension reduction techniques if you detect some noisy variables. The classic R square that you already know measures this kind of effect. But you know that R squared is not. It has some flaws that in the conception. For example, if you add some variables to the model, the R squared increases artificially, and you know that correlation does not imply potential. Some kind of problems with that kind of R squared. But in this case, I won't talk about these problems, but I want to talk about that these methods overlook the geometric structure of the data in the graph. For example, look these two pictures, the model. You have some model like a series with some parameters and a donut a shape of donut. If you apply a linear regression in both cases, the R squared will be you can improve, for example, the first model using a nonlinear function to create a better shape of the data, and maybe you can improve the R squared, but you can do anything with the donut shape. So the R squared will be 0 in both cases. Well, sorry, in both for the linear and nonlinear model. So what can we do? Maybe we can use some other tools like two-dimensional scaling, isomap, or other kind of techniques that uses that geometry and topology of the data in this case. But in this talk, I want to talk about a new index that they're proposing to solve this problem. And our idea is to connect the concept of goodness of fit with the geometry, with the core idea in this case. And to do that, we will use 3 main tools. Basically, is the alpha shapes, the empty space distribution function, and the completely random process or CSR process. Let's start with the first tool is AlphaShape. And AlphaShape is just a filter version of Delanoid translation. So to build an AlphaShape, you need just to build a Delanoid translation for all the data points. And for a given alpha, you filter out all the triangles having a side more than 12. So you extract those triangles from the Delanoid translation, and you can have here the shape. So what is the advantage about an shape? Is that you can reveal little by little the features in the data. For example, an alpha shape with a small alpha, and in this case, you can see a lot of voids and holes in the data, and you don't know exactly what is the shape correct of the data in this case. It's very open. In general, you don't have a exact shape of the data for a small alpha. If you move the alpha to the right spot, you will reconstruct the complete shape of the data in this case. But if you go too far, you will have the complex fault of the data. So basically, you cover all the data with just a point. The second tool is a distribution of the empty space distance. This is a distribution that measures for any U in space how many neighbors you have in a radius R in space. So basically, this distribution measures how the points are distributed in space. It's a way to see. For example, if you have a grid pattern in the data, you will have some function like the first panel. Basically, the points are less than the probability of having neighbors around some points is less than a random process, because you have more structural information in many points. The middle value is basically a random process, a complete random process. And the third one is a cluster data. Basically, for any point, you will have with some radius, you will have more chances of have neighbors around any point, because the points are close. So basically, the idea is just a oversimplified explanation of the theory here, but for the sake of the argument, this is the only that we need. And a complete spatial random process is the third tool. Basically, a complete spatial random process, or CSR process, it has two main characteristics. Is the homogeneity and independence. Basically, homogeneity is that all the points behave the same, more or less, and uniformly the same. And non-point or region has influence over the others. Basically, it's a complete random process in space. Non-point has influence and all are the same. With these properties, you can, for a window W, you can estimate the lambda bar value. Basically, is the number of points on W divided by the total area on W. And this value is basically the density per unit area in a computer. Okay. So with these three tools, I'm going to explain how we build the index. The core idea of the index is this picture. Imagine that you have two patterns, a certain pattern and CSR process. So if you see here, the circle pattern has a lot of empty spaces. After you create the alpha shape or some geometric figure around the point. So the idea is, if all the empty spaces indicate
the presence of a relevance in the data. It means if you have a CSR process here, notice that there is not a lot of empty space around the window. So the idea is to measure how many empty space exist inside your window. So the index will use the alpha shape as the model itself to construct this the blue shape here. The blue shape in the delta shape is the blue shape here. So we'll use the alpha shape as the model. We'll compare this alpha shape with a CSR process to compare if the model is noisy or not noisy. And the parameter of the CSR process will be the lambda bar or the number of points per unit area in the window. So we propose this R squared geometry that is just 1 minus the area of the alpha shape created for the window divided by the area of the W or the window. If you see, this is just a comparison of areas in the structure and the geometry, and the 1 minus is the proportion of the empty space remaining in W using the model of the model A alpha that is just the alpha shape for any points over any other. Now, for construct the index just for a single alpha is not useful because as we did before, using a single alpha just give a picture of how you can reveal the pictures of the data in the time. So the idea is instead of have a single alpha is to construct a function that maps every alpha to the R squared. So we build for any alpha the R squared and see how it behaves. The idea is that the function fi alpha can be seen as discretization of the 1 minus capital F alpha. This function, the capital F is the distribution of the empty space. In this case, 1 minus F alpha, it means the distribution of the filling space. In this case, we are seeing how we fill the space around any point of the shape. For a CSR process, it's very well studied that this function is exponential of minus lambda alpha. But in our case, the function is more scientific than the theoretical one and the estimators. So another thing is to determine if the data is different from CSR process and to construct some kind of confidence intervals for this case. So we generate Monte Carlo envelopes for the CSR process to see if these processes are different from each other. So in this case, it's just estimate a lambda bar for each variable, generate n generated by a Poisson distribution with lambda bar, and we generate n values with distribution x, n values x and y, with distribution uniform for both of them, corresponding in the range, in the corresponding range of each one. And we estimate the function fi alpha for x and y, and repeat this 40 times just to have curves resembling a CSR process and to see how large is the confidence interval for the CSR process. So I want to present some results that is in the paper. Well, a little note about the graphics. In the upper panel, you will see in black the function fi alpha estimated by our index. In red is the theoretical 1 minus capital F alpha, that is just the CSR process, but estimated using the lambda bar in the window. And in gray is the simulated Monte Carlo envelopes for the CSR process. In the middle panel, it's just the discrete derivative of F, just connected via splines for visual aid. This spline does not have any role here, it's just to see how it behaves. And in the lower panel is the function 1 minus a capital F, but estimated using kernel function. And this is important because this is the way that the package stuff uses to do exactly the same analysis for the spatial points. So the idea is to compare how our index behaves with respect to the classic way we do that in R. So this is the first model. It's just a simple model. It has different slopes and different variances. Satoy, for example, you know. But if you see the results of the curve, you will see that, for example, this is the curve R squared beyond, and this is the curve estimated using kernels. And notice that the curve settles down to a value above 0. And that means that the algorithm stops to fill the space until some point because they are alpha shape. In the case of the space stat, basically it says that you are filling the space continuously until 0. So in this case, we have more sensitive. We're more sensitive to the fact that the space is already filled with the shape of the data. And in this case, if you see if the value is more is near to 0, is basically the pattern is near to a CSR. As you see here, so that this kind of pattern is near to a random one than this one, and in this case, you see that exactly the pattern is near to the red one. That is a theoretical CSR process. The third, the second example is this one is just 3 circles, 3 concentric circles, and the second variable, the first variable, and the second variable is a random uniform variable models. In this case, notice that the curve has three bumps that indicates how the circles are filling in each moment, and the second one is near to a CSR product. Basically, it says that the second one is just a completely random product. With the derivative, you can see exactly where the points, where the points where the filling space is occurring in the circle. And this is the most interesting. Using kernels, you can see anything. You can say anything about the circles using the space that the algorithms. So we have more sensitivity here to see where exactly it happening all the bonds in the and the third example is just one. We have 3 circles, leaves, different positions, and shapes. And in this one, we have more or less the same. But if you see the first variable is not as smooth as we have the clear bumps as the others, because the different shapes of the data. Maybe this is a possible workaround here is to use a weighted alpha shape with different radius and for the I explained before. But again, the classic techniques does not include any of this information. And the CSR process is probably. So what is the ongoing research for the future? Thanks to my student Edgar, we are almost ready with confidence interval and hypothesis testing for these objects. We are now almost ready to create this a full inference for this object using maximum specification test with the result, and other is using this CLF test to determine if a data point cloud is a noisy or CSR or not. It's the result. And we are using also multivariate setting using UMAP. I explained before. Basically, here we are projecting the data to UMAP plane, and we can see if the cluster generated by UMAP, we can explore the shape of this cluster, because it's important to see. For example, in this case, it's a data set of smartphones, and we basically we can say the person is standing or walking, and if you see the curves for standing and walking are very different. So we can explain that before. Before. And well, just the last slide. For the future research is construct a functional closed form for A5. Maybe difficult and maybe it's possible, but we need to see. Build a weighted alpha shape to capture different scales. And our idea is to construct a sensitivity index in the sense of the ball based only on the geometric data, analysis of the data. This is my colleagues. This is the paper in statistics. This is a package in Brand already published with all the techniques and
Next talk is a Zoom presentation by George Santos. George, are you ready?
I'm glad to see you.
Thank you.
First of all, I would like to thank this opportunity to present my work with two colleagues from my university. I'm sorry that I could not attend personally, but I still have some health problems, so it was not possible to me to be in Costa Rica, but I'm very sorry for that. I suppose that you are listening okay to me. I can make the talk in Portuguese or Spanish, but anyway, I wrote things in English. So if you wouldn't mind, I would prefer to make my presentation in English. Is that okay?
Sure. You have people that may not speak either Spanish or Portuguese in reality.
Okay. So this is sorry. I have to make sure that it works. Yes. Okay. My presentation is entitled Approximations to the Binomial Distribution, its Bounds, Relative and Absolute Precision. This is a joint work of me, my colleague Marilia, and my colleague Russell Alpizar. We are relating the binomial with the Gaussian distribution. So approximations to the binomial by a Gaussian distribution are not always consensual and can be tedious, especially when we are dealing with probability of a range of extreme values of the random variable. In the last century, some research led to the use of cumulative normal distribution tables. It means that we are using the Gaussian distribution to calculate binomial distributions. Since these distribution tables were very easily available, and nowadays they don't make much sense because it's easy to compute in our PCs the binomial distribution. Anyway, this approximation is best for large samples and evenly symmetric situations. We discussed the three usual criteria for the applicability of this method. First, we have to talk about Abraham de Moivre. It's a very important French scientist, and I took some pictures from the scientific committee for celebrating his 350 years from his when he was born. That's funny that he was born by 1667. He used the Gaussian distribution. Anyway, Gauss was born 100 years later. So we have, well, that's funny. It's not only statistics that de Moivre was found of, he was also found of by instance of complex variables. So this is the Argand representation of complex numbers, but that's not what is the important. The important is that Abraham de Moivre showed that in the limit, these two distributions were very similar. On the left, we have the probability for the binomial distribution, and on the right, we have the Gaussian distribution, the density probability function, and on the left, the probability function of the binomial. The normal curve formula first appeared in a paper by de Moivre in 1733. He wrote this paper in Latin, and in 1938 he translated it himself into English for the second edition of his book, the Doctrine of Chances, one of the first textbooks on probability. That's funny that he enjoyed complex numbers also, and he enjoyed Latin. He wrote the first paper in Latin. Thanks to de Moivre, among others, we know by the central limit theorem that the sum of random variables converges to the normal distribution. A binomial distributed random variable x may be considered as a sum of Bernoulli distributed random variables. We proceed with the use of continuity correction, since it is very easy to implement, and it is recommended and advised by many authors in order to decrease the error. Following approximation will be used. The approximation is very simple. It means that instead of calculating the left probability for the x for this value, we make a correction. The correction is 0.5. Some authors suggest that an approximation of the binomial distribution by a Gaussian distribution should only be made if n exceeded 50 and if the probability of success was between 0.1 and 0.9. And when it's 0.5, it means that the distribution, the binomial distribution is symmetric. So it's easier to, it's closer to a Gaussian distribution that's symmetric also. This leads to a variety, to a valid region represented by a rectangular region in the NP Cartesian plane. I'm going to show, there it is, the Cartesian N we represent it from 0 to 120, and P, the probability of success. This is a Cartesian plan where we have P and N. The first criteria, no, the first criterion, singular, it means that N should be greater than 50. There it is, 50. 50. And should be between 0.1 and 0.9. Of course, we are talking of P probability of success because its complement is key, Q, the probability of unsuccess. So all these considerations, they are very symmetrical. Then we have another possibility that some authors suggest that an approximation of the binomial distribution by a Gaussian should only be made if the expected number of successes exceeds 5. It means NP bigger than 5, as well as expected number of failure, NQ bigger than 5. And that it is the relation between success and unsuccess probabilities. This is a second suggestion that I'm going to show here that says that NP should be greater than 5. That's this blue curve here. And then the other branch related to NK bigger than 5. The intersection of the two gives this region here. It's interesting that this region encloses the previous region. It means that this region contains the previous region. Yes, the rectangular region. Another possibility, finally, other authors suggest simply that variance should be greater than 5. Variance, we all know that's NPQ, and NPQ should be greater than 5. And there it is, and it's a yellow curve here. If we consider recession directions to more infinity in N, that's the region that begins with the yellow till infinity in N. This has some advantages. First of all, it's very easy to state. We just say that variance should be greater than 5. Simple. There is another advantage. That's a criterion that's between the other two. There is this criterion, the rectangular box, there is something that is wrong with it, I think. That's it doesn't trade N for P. It means simply that N should be greater than 50. If we have a sample of 49 with a probability of success of 0.5, it would be located here. It should be rejected by the first criterion, but accepted by the other two. So in my point of view, the worst criterion is this one, the rectangular region. Then I think that it's simpler and wise to stay on the variance greater than 5 criteria. Then we studied something about the errors. Oh, there is another point I forgot to talk about. We can also make an approximation for a Poisson distribution when n is bigger than 20 and the success, probability of success, smaller than 5%. That's the next slide. We can approximate binomial distribution by Poisson when the sample size is equal to or larger than 20, and probability of a single success P should be smaller than or equal to 5%. If n is greater than 100, the approximation is excellent. If NP is also greater than 10, is also smaller than 10. And in the next slide, we show that errors are small, but when we consider the relative error as the ratio between the error and the exact value, it gets very high. By instance, there it is. This is the command for R to get the probability of a normal with 100 tiles and X equal to 10 with a probability of 20%. And the R says that this probability is 0.33%. If we compute, if we approximate by the normal, then we ask for this function, standard deviation form, yes, and we have that the probability of 10 by this approximation would be something like 4.4%. It means 0.44% and here 0.33%. It means that the difference is very small. It's typically 0.1%. But the relative error, here I repeated the same calculation with people that prefers Excel. We are old Excel. We have here the binomial distribution and probability is 0.33%. If we calculate by the approximation, it will be 0.44%. The error, as I said, is typically around 0.1%. But if we talk about the relative error, we will have a relative error of something like 32%. We show that not only sample size and symmetry are important, but also that the error rates are crucial. Small values of the success probability P become unacceptable when we try to calculate tail probabilities. These were tail probabilities that sometimes have the same order of magnitude as the error. With increase of computer capabilities, this is not a practical problem, but the main idea is helping to provide some guidelines to this subject that is pervasive for recommendation to usual introductory probability and statistics courses. I have to tell you that today I've been watching some books, but by instance, some new editions of Agresti, by instance, they do not talk anymore about these approximations. We suggest also that the third criterion to be adopted, since it is easy to state, variance greater than 5 and leads to a smoother domain than the others. I thank the Department of Mathematics and our research center, CIMA, Centro de Investigação em Matemática e Aplicações. Thank you for your attention. I'm available for any doubts I suppose that we still have 2 minutes.
Thanks, George. We will leave questions for the end of the session, if you don't mind. We have some time for that. But in order to keep the time frame, we will pass the word to Luis Grill, who is going to talk about PLS CSIM to assess college student burnout with optimization and stress as predictors. Luis, are you there?
Yes, I'm here, Russell. Just
Okay,
a moment,
thank
please. So, sorry for these technical problems, but thank you very much for having me. So I'm going to talk about an application of PLS-SEM. Okay, and these are the points that I intended to talk about. A short introduction to stress and burnout in college students, the latent variables considered, the questionnaire and the observed variables involved, then the estimator used to estimate the theoretical structural equation model, the evaluation of the outer and inner models, and the multi-group analysis by school and some conclusions. So the high drop rates of college students is currently a concern of universities, which are obviously interested in providing them with the best possible well-being so that their success increases. In recent years, as we know, the students have seen their academic life very limited due to the pandemic and in terms of their social contacts between colleagues and teachers, and the situation maybe reduce their level of optimism and increase their moments of stress, or I should say distress, which is the negative stress. So this situation can lead to the mental health conditions that is being studied and is called students burnout, considered as a result of the continuous and excessive distress that students are subjected to in their daily life. Burnout is a state of emotional, mental, and physical exhaustion caused by excessive and prolonged stress. And Maslach and the research team defined the antithesis of burnout as engagement, which is characterized by energy, involvement, and efficacy. The opposites of exhaustion, cynicism, and inefficacy. And there are other definitions of burnout presented by other authors, but so I think it's enough for this slide because my time is limited. So the main purpose of this study is to build a model for students' burnout, which is the target latent variable, considering optimism and perceived stress as predictors, using a data-driven approach. So having in mind to build a model based on students' perceptions about their optimism and stress and burnout, with these three components, exhaustion, cynicism, and efficacy, implicit in their answers, the structural equation was applied to estimate a cause-effect relationship model with latent variables.
So the main objective is of this research is to investigate which variables have effect on burnout of college students. In particular, we can think in different questions like are optimism and perceived stress predictors of students' burnout? Has perceived stress a positive impact on burnout of students? Does optimism have a direct negative effect on college student stress? Does optimism have an indirect effect through stress on college students' burnout? So we consider the 5 latent variables which are not directly measurable. So we use a questionnaire with the manifest measurable variables that are considered to operationalize these latent variables. These 5 latent variables here: optimism, perceived stress, and these 3 latent variables, which are the 3 principal components of burnout, which is considered. Okay. So in this slide, we have possible links, theoretical cause-effect relationships between the 5 latent variables, which in this case are the same ones considered in the paper presented at the end of this slide, in the bottom of the slide. The theoretical or the conceptual model is usually designed based on specialized literature, as well as considering the empirical knowledge, or I should say accumulated experience of the authors of the project. So here we have the 3 scales or questionnaires that we had considered. One questionnaire or a set of questions for optimism, also another scale or questionnaire for stress, and another questionnaire for with questions related to burnout. These questionnaires were used in Portuguese version, of course, which has also been validated in studies in this research field. And these questions correspond to manifest variables or indicators that refer to the feelings of the respondents measured on a Likert type scale of 5 or 7 points. The categories of the indicators were assumed to be equally spaced and perceived as symmetric. So on optimism, we have these questions, and I would like to draw your attention to just 1 or 2. For example, I'm always optimistic about my future. I enjoy my friends a lot, and so on. Okay. Now the questions related to stress, for example, in the last months, how often have you felt nervous and stressed? And the questions about the core component of burnout, which is the exhaustion. I just consider this latent variable here. Okay, but we also have the cynicism and the efficacy. And for example, I feel emotionally drained by my studies. I feel used up at the end of the day at the university. So the sample and the target population, of course, we combine the questions from these 3 questionnaires into a single questionnaire, okay, with the 35 questions. And it was applied in an online survey conducted in June of 2022 at the Portuguese Polytechnic Institute, where the target population was approximately 2,000 students. The collected sample is composed by 144 volunteer students. It's a non-probabilistic sample, okay, because it's an online survey. And we have almost 60% of the students are from the School of Management and Administration, from these courses, Business and Management, and also Human and Research Management. So the rest of the students are from the Technology School and from the Informatics or Computer Science and the Electrical Engineering. So more some sociodemographic variables, some results. So we have, as I said before, 144 students, and where exactly 50% are women and 50% are men. So the mean age is around 23 years old, with the mean 21, and mode. The standard deviation is 6.2, because as we can see here, we have the minimum is 18 and the maximum 54. So as you can see in this table, where we cross the gender with school, the majority of the students in technology school are men. Okay, as you can see here, we have 57 and 87 from the management school. So on this slide, we have the model presented on a previous slide, which in this case was designed with the smart PLES software. So here we have the optimism, the stress, and the three components of burnout. Now we can see the same model, but where we also consider the manifest variables that operationalize each of the latent variables. Okay, these variables in yellow are the manifest variables that correspond to the questions of our questionnaire. This model is similar to the previous one, but if you look closely, we can see that we have links between the latent variables related to the burnout syndrome. We also decided to consider possible cause-effect relationship between burnout components. For example, this one here, and also this one and this one here, okay? So before presenting the results obtained for the estimate model, allow me to present some theoretical concepts about the structural equation models. There are two types of SEM, the covariance-based SEM, and also the variance-based SEM. So they have different statistical objectives. For example, here, the statistical objective is to minimize the difference between the observed covariance metrics and the estimate covariance metrics, and to test established theory. And one of the estimators is the well-known maximum likelihood method. And here, the objective is to maximize the prediction of the dependent variable and to explore and confirm new theory. And we are going to use, or we used the partial least square, okay, as I said before. So there are important differences between these two family of estimators. And one of them is related to the, for example, here in PLES, it's a non-parametric algorithm, and we don't have a distribution assumption, which is not the case with the covariance-based SEM. Okay, so it is not, of course, it is not convenient for our variables to have very symmetrical distributions, and it is also recommended that the percentage of outliers be a maximum of 5%, which is the case in our study. The PLES also works well with small sample size, which is not the case in the other group of estimators, and so on. Okay, so in this study, we applied the PLES-C estimator, the consistent PLES estimator, as we did in the recent article mentioned on the bottom of this slide, which was published last week, but in the management area, where we identified the most important variables in explaining the internationalization of small and medium-sized companies in Portugal. So there are some advantages in use the PLES-C, which is well calibrated and produce the true parameters values for the models, and performs this algorithm performs a correction of the reflective constructs correlations to make result consistent with factor model, which is the case because our latent variables are reflective latent variables. Okay, in fact, all constructs or latent variables are reflective. So here in this slide we have a structural equation model.
Please, just to remind you, we have 5 more minutes.
Okay, so it's a better idea to skip this slide. Okay, so let me show you that there are some steps that you should verify in order to evaluate the outer and the inner model. Okay, for the outer model we have these steps, and also for the inner model these 6 steps. So we use the bootstrap to evaluate the outer and inner models. We consider the bootstrap non-parametric procedures. We also consider 10,000 subsamples with observations randomly drawn with replacement from the original data set with equal sample size to obtain statistics, p-values, and confidence intervals. And about the minimum sample size, so we use the inverse square root methods, which is a very recent method, and where we consider all these points, the magnitude, the minimum magnitude between these 2 values, the power of the test, the effect size, the level of probability, and so on. So our sample is much bigger than that we need. Okay, our minimum that we obtain according to this method. And so the estimated model, I have the estimated model here on this slide. And, as we can verify the statistical, we obtain this model because this model verify all the requirements of outer and inner models, and we can then see that some links that we had considered in the conceptual model do not appear in this image because they are not statistically significant. We have some links, for example, these links here and also here and here and okay. So all these links are not statistically significant. So if we stretch the model from the previous slide, we get this new representation of the model. And on this slide, we have the standardized estimates of the parameters, past coefficients, and in parentheses, we have the p-values. As we can see, all the coefficients are statistically significant. And in this table below, we have the effect size values, and all of them are statistically significant. inside of the blue circles, we have the coefficients of determinations. We also use the new algorithm PLS predict in order to analyze the errors. Okay, so we use the root mean square error, and as you can see, in terms of this measure, we may say that the model has a medium predictive power because of the negative values shown in indicators for which there is no improvement in the predictive power. We compare our model with a linear model, with a simple linear model, which is the benchmark or a naive benchmark. Okay, ALM benchmark. So here in this slide, we analyze the magnitude of the discrepancies between observed and the expected correlations as an absolute measure of the model fit criterion. Okay, so okay, just one more minute, okay, if you don't mind, Russell. So here I have the two models based on the model that we estimate with the full sample. Here because the data is heterogeneous, we also estimate two models for the two schools, and the biggest difference that we identified statistical difference, statistical significant is here in this link. Okay. And I have these results in this slide, but okay. So let me just call your attention for this last point. The biggest difference is in the value of the pass coefficient, the direct effect between the perceived stress and the exhaustion, which is higher for students in the School of Technology. Okay, and these are the interventions already underway: mini courses, support groups, mentoring groups, access to psychological support, participation of students in social and supporting, and volunteering groups. And some references, and thanks for listening. Sorry. Thank you very much.
Thank you, Luis.
Welcome.
Okay, next is the turn of Rosa. And move to present its presentation and the situational properties of legal certificate. Light on the extreme lower prefecture. Thank you, Mario.
Okay, well, thank you very much, and we finally come to the last presentation of this session and of the seminar. I just like to make an announcement that using a little bit of my time, and maybe at the end of the closing session, if the people in the audience will start open their windows so that we can take a picture for prosperity. And here in the audience, we could stand up here and take a picture for prosperity. Thank you. That wasn't part of the talk, but anyway. So here I'm talking about this Lincoln Peterson-like estimator. And the guy is very simple. We're going back to primary school. And remembering like a simple rule of three. This is a concept that we teach in primary school, so it's nothing new for us, but it's very useful in practice. The idea is the following. I have been interested in estimating animal populations, and counting animal populations is not an easy task because you often don't see everything on the wild. Let's say I'm talking about wildlife.
let's suppose that we have a population of unknown size n. We need to estimate n, big N is in the target. And most of biologists use a technique that is called capture to estimate n. And the intuitive idea of the estimator is this simple rule of three. What do? Let's say you go to the field and you take a sample of size n1. Okay, so you know that you captured or saw n1 individuals in a population of size n that we don't know. That will give you the proportion of individuals that have been seen or captured in the first capture location. Okay, so we know that there is a proportion of individuals. We don't know what that proportion is because we don't know n, but we're trying to estimate n. Okay, so what they do is they go to the second sample in a later time, and they take a sample of size A2. And in this sample of size N2, you expect to see some of the previously seen or tagged or marked individuals. Okay, so you expect to see here some individuals that have been captured or seen previously. We would call that N11. So if certain assumptions hold, we will expect that the proportion of individuals that has been seen in the resampling relative to the proportion of marked individuals in population should be similar. Okay, is everyone with me at that point? So if we expect that, then a simple estimator of the overall n is just, you have this information, and then you estimate n as n1 times s2 times n2 divided by n11. And that's why it's called a simple input estimator, and is the basis for a large class of methodology. And this is intuitive, but the mathematical part of it comes now. If we think of n11 as a random variable, as a discrete random variable, let's hope that it's not zero, but it could be zero sometimes, or it could be small sometimes. And that's a problem for this estimator, because we can, if this is zero, we cannot compute this variable. It's infinite. Okay? So that's has been studied a lot in the literature, and the motivation of the work I'm going to show is that most of the time when this n11 is low, this estimator varies a lot, and the properties become very difficult to understand. Okay, so if it's zero, it's a problem because it's undefined. Okay, so one simple way to put mathematical frame on this is to think about this n11 as a random variable. The simple thing to do would be, let's think about the binomial of a sample of size n2 with the probability of detecting the animal p, where p is simple the proportion of individuals that have been marked. Of course, we don't know that, but we're trying to estimate it, right? So if we think like that, then we can, and if we know this estimator, then what we have is the inverse of a random variable that is binomial. And how is the behavior of the inverse of a binomial random variable? In fact, we are interested in a non-zero or a truncated binomial random variable. And then, one may think, yeah, but that's very rare to happen. But here is a study by Ann Chow, where she's doing an application to human population, because certain human population behave wildly, like we don't know how they behave. And let's say if we want to estimate the number of individuals with a weird disease, or now with COVID, if we want to estimate the unseen individuals, the ones who were asymptomatic. So the same idea that what they use in wildlife, capturing individuals, we can use
if we have lists of individuals in a human population, but we don't count all of them. So we want to extrapolate how many we don't see. So let's say this is a paper published in Biometrica Journal, and here they're trying to estimate drug users. And basically what they do is they have two lists. One list that comes from prison and judicial list, from all record from the intoxication individuals, and the other is from the list of hospitals. So they match the two lists and they try to see how many overlap. And these are the ones, sort of like the one that has been recaptured. Okay? And look at these very low values. So if we try to estimate using the Lincoln filters, this estimator is going to vary a lot. And if we have 0, we have a problem, right? But anyway, so basically a lot of work have been done, as I say. And back in the 1951, Chapman came out with this modified Lincoln filters estimator that avoids having 0 here. Why? Because he had 1 to all the quantities. And then we get the estimator, and that's not a problem in terms of expected by the variance N11 is 0. So anyway, he studied the properties of this estimator using a hypergeometric model, thinking of N as a hypergeometric distribution. And there are important assumptions why we would prefer hypergeometric and not a non-binomial, and have to do with the assumptions of each one. Anyway, so Baylis, around the same time, look at this estimator who avoids also the 0 problem and use the binomial approximation to the hypergeometric. Notice is that if we have, I'm going to include some more notation here. We will have here that N10 will be individuals that were seen in the first sample, but not in the second sample. And here we have N01 individuals that have been seen in the second sample, but not in the first. Okay. So if we think of this triple, N10, N01, and N11 as a multinomial distribution, then we can study again the properties of this estimator based on a multinomial distribution, which sometimes is more realistic because all of these quantities are random. Okay, so this, like I said, this has been estimated. This is another estimator that was proposed by Shao in the 1987, and she based this estimator on a concept that is called coverage. So back a few years ago, I had an undergraduate student, and she did some simulation exercise looking at the behavior of that estimator. That was Christina George. And what happened is that if we have a small populations, even with probabilities of capturing as 20% in the first and the second sample, we have a lot of problems with the performance in some cases. You know, like 60.5% under these situations were undefined. We could not estimate that being completely. So it's have poor performance if that's the case. And again, you know, the properties say that Chapman performed a little bit better compared to the Lincoln, who is have worse performance, and the Bayesian. This is because of this variability. So we now have Alicia Rodriguez in the department, and she came a few years ago to the department, and she's specialized in extreme value theory, as she had already spoken. And then thinking of this problem, I was thinking, well, this is a problem of extreme value theory, where we are interested in the behavior of estimator with minimum values of any of these distributions. It's not the maximum, as most extreme value theory have been developed, but it's with the minimums of a discrete known distribution. So we start looking at that, and in the literature, it's interesting But there no zero truncated distribution has not been looked at. Why not? Why do we have to use these tricks of adding one? If we have zero truncated distribution, we can look at the behavior of the zero truncated distribution, or if it was one truncated distribution. And then we start working on this. And as Ligia already mentioned, the distribution of the minimum can be easily studied from the distribution of the maximum. If you have sequence from the variable multiplied by minus, and then you give the opposite direction, and then. So, yeah, some issues. Zero truncated distribution will avoid the undefined or in definition of the estimator. Not much has been saying in the literature. It's interesting because I was expecting more of it, about the behavior of the inverse of positive discrete random variables. If we go and look at the literature, there are problems there. And then, as I already say, the distribution of the maximum, there are some results, and we're going to apply it to the distribution of the minimum. But we have no cross form from the distribution. Specifically, there is no way to get it in cross forms. Okay, so we have to do some simulations. So interesting is that we are talking about the inverse of a random variable, and it's a discrete positive random variable. So if we have monotonicity, we know that the probability of y will be equal to the probability of x. Because we have discrete points. Right? So if I put y, then the probability of the inverse will be the same. The probability will remain. So in the case of the zero truncated binomial, if we look at the inverse, we have 1 over a, 1 over 1, up to 1, and we have a jump here, which is very weird, right? We don't get, if we're looking at discrete, we jump. If n goes to infinity, then we are going to come to 0, which is very interesting behavior. This is the binomial have finite support on n, but the Poisson have infinite support, right? So we know that. So this is some simulated just simulation here. And what we did was to look at the zero truncated, accumulated 1,000 observation for some small sample size, and equal 10 and probability of the first capture equal 0.2. If we look at the distribution of the inverse, we look something like this. Look at the jump. And then this is clumping. If we look at the zero truncated Poissons, well, it's similar behavior for the same parameter. Okay, now we land there is 2. Now, if we compute the Lincoln, Chapman, Bailey, and Chow estimates, and look at the empirical distribution of those estimates, this is what happened. This is the true value of n. Let's say n here is about 50. And look at here the variation of the Lincoln, Peterson, and the Chow that admits n11 in the denominator, and this that make that ratio +1, right? So this is better behaved, but we know that these are biased low, where this is unbiased. Okay. Well, similar situation with how are we doing the time? Okay. Now we increase sample size to 40 and same probability of capture, and this is what happened. Just going from n to equal 10 to equal 40, things become much better. Although we have some quite extreme values here in the tails of this, in the tails of the distribution. If we will look at the distribution outside of this extreme value, that need careful consideration, we will have sort of, again, the Chow and the Lincoln are unbiased. Careful, I say about it, right? And then we have this a little bit more biased. This is, and here is the inverse of the distribution of the inverse. But anyway, so this is for one sample size, for one row. But what happened with the distribution of all minimums. Well, now we're going into the extreme values here, right? What is the behavior if we take many samples from the distribution and take the minimum for each sample and look at the distribution of those minimums? Okay, that's where I say we don't have theory about that. There is some theory developed on for some case. Yeah, and we try to adapt to the binomial case. And this is what happened. This is the distribution of the maximum as n goes to large, and this is the distribution of the minimum. Okay, and this is if it's Poisson, and this is if it is binomial, and these are exact distributions. Okay, we're not using as in here is the exact distribution. Okay, so a very simple problem. A very simple idea brings us to very complex concepts. And what we have here is this is work in progress. We're still working on this. And what we have is that the behaviors of an inverse zero truncated discrete random variable, little is known, and even less to the distribution of the minimums of those variables, or to the inverse of that variable. One different approach will be to consider the probability of P. Instead of looking at the discretization, let's see what happened to P as P goes to 0 or as P goes to 1. And let's think about P as a beta distribution with certain parameters. And then this is a continuous variable, and more theory has been developed in extreme value theory for continuous variable. We was talking about that today. So this will be an alternative approach. The other approach will be to use the Bayesian approach to look at the distribution of these variables. That's all I have to say. Thank you. How we very good. So we are coming to the end of the talk, and we are to the session to the whole workshop, and we're going to have a closing ceremony where we have two speakers, and they are the center directors. We have questions. The other day I was also skipping even some participants. Apologize about that. That's true. We have session for questions. Any questions? Either from the audience or from the audience in the Zoom platform, or for the audience here in this entity. I have a question. Okay. If you want to stand up here and ask the question for Michael, it's good.
You use as a null model the CSR. Have you tried the null model instead of CSR?
No, because the CSR for the literature that we review is the impacto model that is for but we can use others
because it has a lot of structure.
Is it financial? In case yeah, that in the plane you see that as in the distribution function in the space you see that as different distribution.
And you compare with the kernel based method.
Yeah.
It's a Gaussian kernel based.
I didn't review that exactly. Yeah, I use the default parameters.
Okay, so
the space and the package. So I didn't review exactly.
So I think it's not.
Yeah, I think. I have a question for you also. When
when you do the density of the points in the Cartesian plane, you have clumped points sometimes, right? Where you have different sort of like special distribution. That's what we were trying to do. But I was wondering if you can tie some of that theory to the issue of special distribution of points. To measure, just to measure, when you say density, you have a lot of points very concentrated, but you can have points dispersed. If you have repetitive points, how do you measure that density? Because they are complex. You know what I mean?
Yeah, we can measure that using, for example, in delta shape. You can measure with the size of the triangle. Because if the data is very close to each other, the triangle formed the delta shape as a small. If you have 2 points or 3 points in very things, very large distance, the triangle forming these 3 points are very large. In fact, we can create I did some time some experiments, so we can create some density estimator using only the size of the triangle. Become more or less more of the density.
Further questions, comments?
I have a question for you. In the minimum, if you have some formulas to the minimum, same way of maximum for the feature depend. There are some formulas, three value term, the formula for the maximum. You have something similar for the minimum.
Yes, you can use the same. You can do that symmetry, the asymmetry, let's say. You can use the same, at least for the theory that has been developed in the stream by theory. Maybe Ligia can respond better that.
Sorry, can you repeat the question? I wasn't listening.
The question is if the formulas that have been developed for the maximum in extreme value theory, they apply as well for the minimum.
Yes, we have to do a transformation, but they apply.
The problem with,
But can you specify what you want to do is it a parametric approach, a semi-parametric approach? Because
general, general question.
As a general question, yes.
The problem with this variable that we have been looking at is that we don't know in which case they are degenerate distributions, and that's technically but zero. Yeah. You have other questions there in the chat? Any more questions? Well, now I will retake that. We are coming to this closing session, and we have the two center directors giving us a few words about how they see the future of our collaboration based on the protocol that will design and ideas of how we can move forward with these synergies. Professor Munoz, please.
Okay. Well, first of all, I must thanks to the organizing committee, not only, but also to the staff here in the CIFAR and to CIFAR in general, and the colleagues in general for the kindness and the warm way as we were received here in the University in Costa Rica. Thank you very much. And in fact, during these 3 days, we assist to set very good level talks and communications. And I suppose nowadays we have a more precise idea what CIMA and CIPA research field they are developed in both centers. Nevertheless, I would like to make a quick overview of CIMA to have a more precise idea. So the CIMA research are split into 4 research groups and 2 research lines. The 4 research groups are differential equation optimization, logic, algebra, and geometry, dynamical systems, statistics, stochastic process and applications. And we have seen here several talks of each of these groups along the 3 days. The 2 research lines. Research lines means that they are kind of interdisciplinary. So we have research from different groups working in this research line with a specific goal, specific tasks, and we can have here even researchers. They are not mathematicians, but in other areas. These are the 2 research lines: mathematical model and life science and applications, and mathematics and application to technology and industry. That's the research line I will mention a few moments in the break. Quick things in each group. For example, in this differential equation optimization, we have boundary value problems for ordinary differential equations, calculus of variations, non-small analysis, partial differential equations, numerical methods, and multi-objective optimization. So we have a lot of areas inside this group. But this group, we have numerical, logic, algebra, and geometry, numerics in groups, logic, Artinian algebras, tensors, and Artinian Goldstein algebra. I hope that I pronounced it the right way. And we assist also in these days to several communications in this area. For the dynamical systems, there are a very variety of themes, like models to study the spreading of forest fires, chaotic dynamical systems, some convexity conditions, some models related to tourism, models to study the movement of loads to grains, and forest management for some wildfire risks. And for the statistic and stochastic process application, we have also a variety of themes and fields in this area, like the stochastic process applications, survival analysis models, some systems to study the environmental risks due to floods and fires, a model to predict road traffic accidents in some region of Portugal, some regression models, and the application of statistical methods of data analysis. We saw also several implementation and communications in some of these fields. In the research lines, we have, as I mentioned, a kind of interdisciplinarity work. We have here some individual projects with specific goals and specific tasks. There, people could be in or outside the CIMA, in or outside the mathematics, let's say. So it's a kind of interdisciplinarity area. The tasks are trying to solve some problems, some questions, optimizing some tasks proposed by some institutions or by associations. We have also what we call the complexity laboratory that allows to experimental to test some conjectures in let's say laboratory way. So I suppose now from CIMA and I suppose from CIMA too, we have more precise ideas what we can do in the future. And I have some ideas that I will propose here. For example, a way that people to improve and increasing the collaboration and the communication between CIMA and CIMPA is to invite it, to allow, and to wish that CIMPA researchers take part of our joint weekly seminar, joint between the research center, the department of mathematics and the PhD program. This is online, so all of you are invited already to take part in this seminar. But I will ask also, if you don't mind, for the direction of CIMPA and the administrative part, we will send invitations and let's say the media for the title of each weekly seminar. If you can attend, we have the link Zoom, and moreover, it was the participation of CIMPA researchers will welcome here. And where the proposal, I hope that you will agree that in 2025 we make a second workshop in applications now in Évora, and you are already invited to go to Portugal and Évora in 25. We will arrange and the date the more convenient date for you and for us, and we'll check this part. And of course, we can have some research collaborations. I saw here in several areas, statistics, in algebra, in the differential equations, that there are common fields that we can make some collaborations. But I suppose CIMA and CIMPA will profit this collaboration, and which will be very useful for each research center. And of course, we could have some mobility researchers and PhD students. Now we have already someone that are interested in our PhD program, and you are welcome in Portugal. And of course, we are open to other suggestions that someone could have some ideas, and we are open to this collaboration, because I suppose for the first one, we started in a very, very good way. That's all. Thank you.
Thanks, Dr. Jimenez, for the words and also for the also remarks that you shared with us. I think from the beginning, once I was visiting your website and everything, it's very interesting how the different research lines they are shared together. So we are several research topics in common. For example, geometry, algebra, also differential equations, some ideas, and common lines. and of course statistics and probability. I think just to give an idea of the first words I gave at the beginning of this workshop, we are centering in ground, so we are growing a lot from I think like 2 years or 3 years ago, and we have a very young population in terms of research. So the people are coming in his 30s or even 20s to do some research here, and we are in route, and we have very common ideas with respect to CIMA. So as Dr. Munoz mentioned, for example, in geometry, in algebra, we can do a lot of things. I think we have very good researchers in those areas, and I have spoken with some of the researchers in CIMA, and I think we can see the future a common ideas in that kind of areas, theoretical areas, and of course in applied areas. So I will give just some brief words about closing remarks here in SIMPA and CIMA about this workshop. And so what did we learn in this kind of workshop? First, it is possible to combine in just a 3-day, it's just a couple of, 4 hours per day, 3-day event. It's possible to combine different research areas in mathematics and applications. It's possible to do it because some people just give you a very broad idea that it's impossible to do that, but it's possible. This is the proof that we can do it. And also because of the pandemic, we learned a lot, and we learned how to do hybrid events, and we are in that process. So we know we have to find more resources in order to do a better hybrid event in the future, and also all the seminars. We want to do all the seminars in the future in SIMPA in a hybrid way, so we can share, for example, the links with CIMA, and we can do that kind of events in common. That's what we are planning to do in the future. And also the time zone challenges, they are not very important, but I think from the hybrid point of view, it's something we have to consider. So if we want to share, we want to invite someone else from another time zone, it's possible to do it also. Future challenges. We want to create collaboration environments, of course, is what Professor Munoz is talking about at the beginning. So there are some common research questions, and we can create some common research questions, but I think we have to create new research questions beyond research areas. So I think if people from algebra can do collaboration with people from statistics. And here in SIMPA, we have an example with Michael and Alberto. Alberto is from algebra, Michael is from statistics, and they actually, like, I don't know, like 3 months ago, they published a paper, and they are doing some interesting results, interesting research in topological data analysis, for example. And I think CIMA and SIMPA can do that kind of stuff. So we can try to combine people from different research areas and try to question or try to answer some interesting new research questions. Also, we have to look for an active involvement of the students. So not only master students, only PhD students from CIMA, and we don't have PhD in mathematics here in UCR, but it's one thing that we have to plan for the future. I think this kind of involvement between different centers, research centers, can produce as just as a product. We can have some kind of PhD program in the future. It's what we are. We have PhD in science, but maybe we can have something more specific in mathematics, something more involved with the research we do in SIMPA, for example. And also we can try to develop new research areas. For example, in SIMPA, industrial mathematics is what we were talking about. The research line that you have in SIMA, we can learn a lot about your experience in that kind of involvement with industry in general, like engineering, not only banking or finance. We can look for other type of products or other type of research areas like industrial mathematics, like engineering applications and something like that. Next steps, I think we are on the same line, so we are thinking about the same thing. We can do some thematic seminars, joint thematic seminar, for example, in algebra, geometry, in statistics, in differential equations, is what we can do. I think is the closest step, I think, to do that kind of seminar. Also, we can do some co-advising with PhD and master students. We have master students here. In the future, we can have more PhD students. We can have a PhD program. So maybe we can do some co-advising between CIMA and SIMPA, mobility of researchers between CIMA and SIMPA, and of course, what we are thinking about the 2025 to organize a workshop in the future in Portugal. So we are in the same steps. We are in the same line. I think we have to work. And I finish with this very known quote of Henry Ford. And I think we have to just work and to do that kind of ideas and to create everything. Thanks a lot for your attendance, and I'm very, very glad to have you here in Professor Munoz and also Rosel, and to have you here in Costa Rica. Thanks a lot. When we have a present for you. Profesor Muñoz, voy a hablar en español.
Va a ser eu fico pouco sem jeito, porque não trouxe nada para você.
No hay problema, no hay problema.
Thank you very
Muchas
much.
gracias.
Viste, se uma foto, consegui ver com foto.
Muy obrigado.
Muito obrigado. Muito obrigado. Está sintonizado, né? Estamos no mesmo, na mesma via, sempre. Temos anos de vontade. Sim, sim, mas já vai por dentro.
Okay. Todos nos llevamos después. Tal vez tomamos la foto primero.
Yo quería que le diéramos también el medio.
Claro, claro. Había una pausa de risa en la película.
A ver si vamos a tomar una foto aquí. No sé si te diga a la muchacha ya fue que gustó.
Sí, todo dice que pues no me la sala, ya que tienes que tener la cámara.
Pueden encender la cámara, ¿quién le falta ahí? No seríamos nosotros.
No.
Tal vez no está ya ahí.
No, sí,
A veces no está.
José Ramírez,
Brillo. Oscar está poniendo, ¿no? Y el artista
José Ramírez.
el artista está aquí. El Bruno está en este momento ahí.
Entonces, no, es que bien. Aquí a la parte de Alex.
Aquí a la
Ya lo topé, Alex. Para eso.
No, pues, eso lo podemos quitar, porque no hace falta que esté en imagen. Sí, cierra la imagen. Exactamente, ahora sí ya no está más adelante.
Ya no estamos ahí. Ahora sí.
Vamos, ya vamos.
Hasta tres, lo que son. Ahí, una ahí, y luego. Aquí en la cámara, ahora fue parte del. Ahí, a toda la cámara. Alguien se fue, ah.
Gracias. Y los que gusten van a ir a comer a restaurantes de tierra. A la plaza, a la parte. Vamos a hacer. Hay reservación.
¿Para cuándo?
Luego se prepara bien. Bueno, y la entrega ahí simbólica, ¿verdad? Los certificados. Ustedes ya
para llevar.
son todos los de Portugal. Ajá, los de Costa Rica.
Ok, y el mío. Va para Portugal.
Papá, Portugal. Muchas gracias por aunque, bueno, es que no, porque ya le iba a decir que me venía aquí, me venía acá, pero a la una tengo reunión. Y a las 2 y a las 3 también. A la 1 tengo con el coordinador de TCU. A las 2 con Javier y a las 3 Sí, yo creo que si quieren ir, o si quieren.
Sí, disculpe. Ellos están oyendo.
Sí.
A los colegas que están en Portugal o en la plataforma son. Muchas gracias por la. Thank you very much for your participation to all of you. And thanks for making all this possible. We're going to close the session now. Thank you. And we read your comments, Carlos. Thank you.
Gracias.
Fernando, thank you very much for all the support.